Hello, sleepy soul, wherever you are in the world tonight. Welcome to this quiet corner of the universe, where the night sky holds secrets so vast, so impossibly heavy, that your own worries, your own thoughts, begin to feel wonderfully light by comparison. If you're here, it means you're searching for rest. Perhaps sleep has been difficult to find. Perhaps your mind has been racing, turning over the concerns of the day, the week, the year. That's all right. You've come to the right place. Tonight, we're going to drift together through the cosmos. We're going to explore neutron stars, those strange, dense remnants of stellar death that spin silently in the darkness between galaxies. We're going to learn about them slowly, gently, one fascinating fact at a time. There's no rush. There's nowhere you need to be. Nothing you need to remember. Let your eyes grow heavy if they wish. Let your breathing slow. You have permission, complete permission, to stop thinking, to stop planning, to simply drift. The facts will continue, whether you're awake or asleep. They'll be here, a gentle voice in the darkness, describing wonders so far away and so long ago that time itself seems to slow down. So settle in. Adjust your pillow, pull your blanket a little closer, and let's begin our journey into the deep, quiet cosmos. Neutron stars are among the strangest objects in the universe. They're what remains when massive stars die, when a star much larger than our sun reaches the end of its life. When it's burned through all its fuel, it collapses, and in that collapse, something remarkable happens. The star doesn't simply fade away. Instead, its core, its very heart, compresses. It compresses beyond anything we can truly imagine. It becomes so dense, so impossibly compact, that the very atoms themselves break down. Protons and electrons are crushed together. They merge. They become neutrons. And what's left is a neutron star. These objects are small, impossibly small for something that once was a star. They might be only 20 kilometers across, about the size of a city. Manhattan, London, Tokyo. Imagine an entire star, compressed down to something you could drive across in less than half an hour. But despite their small size, they are heavy, so heavy that our minds cannot quite grasp it. We'll explore that heaviness tonight. We'll sink into it. Let it ground us. Neutron stars spin. They pulse. They sing with radiation across the electromagnetic spectrum. Some are quiet. Some scream with energy. But all of them are beautiful in their strangeness. Tonight, we have 60 facts to explore together. 60 windows into these cosmic lighthouses. We'll move through them slowly, one by one, letting each fact settle before moving to the next. There's no test at the end. No need to remember anything. Just let the words wash over you. Let the vastness of space, the incomprehensible density, the billions of years, let it all make your own concerns feel smaller, lighter, less urgent. Breathe, relax, and let's drift into the first fact. Imagine, if you will, A teaspoon, an ordinary teaspoon, the kind you might use to stir sugar into your tea. Something small, something light, something you could hold between two fingers without effort. Now imagine filling that teaspoon with neutron star matter. If you could somehow scoop up a teaspoon of material from the surface of a neutron star and bring it back to Earth, that single teaspoon would weigh around 1 billion tons. 1 billion tons. To put that in perspective, that's roughly equivalent to the entire mass of humanity. Every person on Earth, all 8 billion of us, our combined weight would equal a single teaspoon of neutron star material. Think about that for a moment. Every human being who has ever lived, every child, every elder, every person going about their day, all of us together, compressed into something you could hold in your palm. It's a weight beyond comprehension. And yet, the neutron star holds its density across its entire body. Every teaspoon, every cubic centimeter, all of it impossibly, unimaginably heavy. But the neutron star doesn't struggle under this weight. It simply is. It exists in perfect equilibrium, balance between the crushing force of gravity and the resistance of quantum pressure. It has been this way for millions of years. It will remain this way for millions more. There's something calming in that, something peaceful. The neutron star doesn't worry. It doesn't rush. It simply spins in the darkness, holding its impossible mass, and endures. Let's stay with this idea of density for a moment. Let's let it really sink in. Neutron stars pack 1.4 to 2 solar masses into a sphere just 10 to 20 kilometers across. What does that mean? It means that the entire mass of our sun, that brilliant ball of fire that lights our days and warms our world, that massive sphere that you could fit over 1 million Earths inside of, all of that mass is compressed down into something the size of a city. Neutron stars are denser than atomic nuclei. Think about that. An atom is mostly empty space. If you took away all the empty space in your body, all the vast distances between atomic nuclei, you would be smaller than a grain of sand. But a neutron star is denser even than those tiny atomic cores. A sugar cube of neutron star material, one of those small white cubes you might drop into coffee, would weigh as much as Mount Everest. Mount Everest, the tallest mountain on Earth. 8,849 meters of rock and ice. Millions upon millions of tons of stone. All of it in a cube you could balance on your fingertip. The mind struggles with this. That's all right. Let it struggle. Let the impossibility of it wash over you. There's no need to understand it fully. Just know that it exists. Out there in the darkness between stars, these dense remnants spin and pulse. They've been there for eons. They'll be there long after we're gone. Solid, dense, eternal. If you could somehow stand on the surface of a neutron star, though of course you couldn't, you would experience gravity unlike anything imaginable. The gravity on a neutron star surface reaches 2 times 10 to the 11th power times Earth's gravity. Numbers like this become abstract. Let's make it concrete. Let's bring it down to something we can almost grasp. If you weigh 100 kilograms on Earth, a fairly average human weight, on a neutron star you would weigh 20 billion tons. 20 billion tons. You would be crushed instantly, flattened into a layer of atoms less than a single atom thick. You would become part of the star's surface, indistinguishable from it. But imagine, just for a moment, what that gravity would feel like. Every cell in your body pulled downward with inconceivable force. The very atoms of your being compressed together. Time itself would slow for you relative to someone watching from far away. Of course, this will never happen. You are here, safe, in your bed, under your blanket. The gravity holding you is Earth's gentle embrace. Just enough to keep you grounded. Just enough to feel secure. The neutron star's crushing grip is far away, impossibly far, light years distant. It cannot reach you here. You are safe. You are light. You can rest. Inside a neutron star, in the deep interior where pressure becomes almost unimaginable, sound behaves strangely. The speed of sound through matter depends on how stiff that matter is, how resistant it is to compression. On Earth, sound travels through air at about 340 meters per second, through water, faster, through steel, faster still. But inside a neutron star, where matter is compressed beyond anything found anywhere else in the universe, where quantum degeneracy pressure holds the star up against collapse, the speed of sound approaches the speed of light itself. The speed of light, that universal speed limit, the fastest anything can travel. 186,000 miles per second. Sound vibrations in matter, moving at nearly that speed. This is where relativity takes over, where the normal rules of everyday physics bend and stretch, where Einstein's equations become necessary to describe what's happening. Inside the neutron star, matter is so stiff, so resistant to further compression, that ripples and waves propagate through it at nearly the ultimate speed. It's a limit, a boundary. The universe's rules, and even neutron stars, dense as they are, cannot break them. There's something restful in that. The universe has laws, boundaries, limits. Within those limits, everything unfolds. Stars are born. Stars die. Neutron stars spin. And we rest. Light does strange things near a neutron star. The extreme gravity bends light rays, curves them, redirects them around the star's surface. If you could float above a neutron star and look down at it, you wouldn't just see the hemisphere facing you. You would see more. You would see partway around the back. The star's own gravity would bend light from the far side, around the edge, into your eyes. This creates what astronomers call a shadow region. Areas that should be hidden from view, but aren't. The Event Horizon Telescope, the same instrument that photographed the black hole at the center of our galaxy, has modeled these effects. From some angles, you would see more than half of the neutron star's surface, the front and part of the back, simultaneously. Space itself is curved around the star. Light follows those curves. It's as if the neutron star sits in a depression in the fabric of space. A well, a pit, and everything around it, even light itself, must acknowledge that curve. This is gravity's nature. It shapes space. It guides light. It dictates the paths of everything. And we, lying here in the gentle gravity of Earth, we feel only the faintest echo of these forces, just enough to keep us grounded, just enough to feel the mattress beneath us, the pillow supporting our head. Breathe, settle, let the curved space of the cosmos hold you. When light escapes from the surface of a neutron star, it must climb out of that deep gravitational well we just described, and climbing costs energy. As photons, particles of light, struggle outward against the immense gravity, they lose energy, and when light loses energy, its wavelength stretches. It shifts toward the red end of the spectrum. This is called gravitational redshift. For neutron stars, this redshift is substantial. Light shifts red by factors of 0.2 to 0.4. If a hot spot on the neutron star's surface emits blue light, by the time that light reaches a distant observer, it might appear green, or yellow, or even red. Astronomers can measure this. They look at spectral lines, specific wavelengths emitted by hot atoms, and they see how much those lines are shifted. From that shift, they can calculate the strength of the neutron star's gravity. They can estimate its mass, its radius. The universe reveals itself in the stretching of light. This redshift is constant, eternal. For as long as a neutron star exists, for millions or billions of years, every photon that escapes will be shifted, slowed, reddened. It's a gentle process. The light doesn't struggle or strain. It simply changes, adapts, continues on its journey, slightly altered. Rest now. Let your thoughts shift. Slow. Redden into sleep. Neutron stars are not ancient knowledge. They are a recent discovery in the grand timeline of human understanding. In 1934, just 90-some years ago, two astronomers named Walter Baade and Fritz Zwicky made a remarkable prediction. They proposed that when massive stars explode as supernovae, the core doesn't disappear. It doesn't disperse into space. Instead, it collapses. It compresses. And what's left is a neutron star. This was only 2 years after James Chadwick discovered the neutron itself. The neutron was still new. Its properties were barely understood. And yet, Baade and Zwicky realized that if you could squeeze protons and electrons together, force them to combine into neutrons, you could create an object of immense density. They predicted this from theory alone, from mathematics, from understanding gravity and quantum mechanics. They had never seen a neutron star. No one had. But they knew such objects must exist. It would be decades before their prediction was confirmed. decades before pulsars were discovered and recognized as spinning neutron stars. But they were right. The universe was exactly as strange, as dense, as fascinating as they had imagined. There's something beautiful in that, in the power of human thought, to predict the universe, to imagine what must be, and then, years later, to find it. We are small, brief, but we can understand stars. We can dream of neutron stars and have those dreams confirmed. Rest in that knowledge. You are part of a universe that makes sense, that follows rules, that rewards patient observation. Let's go back to the moment of birth, the moment when a neutron star is created. A massive star has run out of fuel. For millions of years, it has burned hydrogen, helium, carbon, oxygen, element after element, climbing the periodic table. Each burning creates energy, light, and heat that push outward, supporting the star against its own gravity. But eventually, the core becomes iron, and iron won't burn. Iron won't fuse into heavier elements and release energy. Iron is the end of the line. Without energy pushing outward, gravity wins. The core collapses. In less than a second, a sphere larger than Earth crushes down to the size of a city. The density becomes so extreme that protons and electrons, which normally repel each other, are forced together. They combine. A proton and an electron merge. They become a neutron, and in that merger, a neutrino is released. Neutrinos are ghost particles. They barely interact with matter. They can pass through the entire Earth without touching a single atom. But during a supernova, so many neutrinos are created, trillions upon trillions of them, that even though most escape freely, some interact. Those interactions deposit energy in the outer layers of the star. They help power the shock wave. They help drive the explosion. The escaping neutrinos carry away vast amount of energy. More energy than the star is radiated as light in its entire lifetime. They stream outward at the speed of light, invisible, undetectable by anything except the most sensitive instruments. And what's left behind is the neutron star, dense, hot, spinning rapidly. A newborn object in the cosmos. This happened billions of times throughout cosmic history. Stars have lived and died. Cores have collapsed. Neutrinos have streamed outward. And neutron stars have been born. They spin now in the darkness. Ancient, patient, slowly cooling. Just as you will cool now, your body temperature dropping slightly as you relax into sleep, your metabolic rate slowing, your breathing deepening. Rest. The universe is vast. You are safe. The collapse of a stellar core is not smooth. It is not gentle. When the core of a massive star collapses, crushed by its own gravity, it falls inward faster and faster. The outer layers plummet toward the center at speeds approaching a quarter of the speed of light. But then, the collapse reaches nuclear density, the point where matter becomes as dense as the nucleus of an atom. And at that density, matter resists. It pushes back, quantum degeneracy pressure, a purely quantum mechanical effect, suddenly becomes important. Neutrons cannot be compressed further. They occupy the lowest energy states available. The Pauli exclusion principle forbids further collapse. The core bounces. It rebounds elastically, like a ball dropped onto concrete. The infalling material, moving at tens of thousands of kilometers per second, suddenly encounters an incompressible wall and bounces back. This rebound launches a shock wave, a wall of pressure and energy that propagates outward through the star. This shock wave, combined with the energy from neutrinos, blows the outer layers of the star into space. The supernova explosion has begun, and at the center, still and dense and impossibly compact, the neutron star remains, born in violence, born in a moment of catastrophic rebound. But now, millions of years later, those neutron stars are peaceful. The chaos of their birth is long forgotten. They spin quietly in the void. Everything calms eventually. Everything finds equilibrium. Even your racing thoughts. Even your busy mind. Eventually, with time, with patience, they settle. Let them settle now. In the first 10 seconds after a neutron star is born, it outshines the entire visible universe. Not in light. In neutrinos, the newly formed neutron star is unimaginably hot, tens of billions of degrees. At these temperatures, the core is a roiling sea of neutrons, protons, electrons, and neutrinos. The neutrinos, created in vast numbers during the collapse, stream outward. They carry away 99% of the supernova's energy. 99%. The brilliant explosion we see, the light show that can briefly outshine an entire galaxy, that's only 1% of the energy released. The rest, the vast majority, escapes invisibly as neutrinos. For those 10 seconds, the neutron star is the brightest object in the universe in neutrino light. If we had neutrino eyes, if we could see in that invisible spectrum, a nearby supernova would be blinding. But we can't see neutrinos. They pass through us, through the Earth, through everything, unnoticed. Only rarely, very rarely, does a neutrino interact with an atom in a detector. And from those rare interactions, scientists can reconstruct what happened. They can measure the neutrino burst. They can learn about the birth of the neutron star. In 1987, a supernova occurred in a nearby galaxy. Supernova 1987A. For a few seconds, a burst of neutrinos passed through Earth. Detectors in Japan and the United States recorded about 24 interactions. Just 24 from a flood of trillions. But it was enough. Enough to confirm the theory. Enough to prove that neutron stars are born in neutrino fire. Those neutrinos had traveled 168,000 years to reach Earth. They passed through the planet, through rock and water and air, and only a handful stopped. The rest are still traveling, spreading out into the cosmos, carrying the news of a star's death into the eternal dark. Rest now. Let the invisible particles of the universe pass through you. They do not disturb. They do not wake. They simply pass. Not every collapsing stellar core becomes a neutron star. There is a limit, a boundary, a point of no return. If a stellar core is heavier than roughly 3 times the mass of our Sun, even the quantum pressure of neutrons cannot hold it up. Even degeneracy pressure, that fundamental quantum resistance, is not enough. The core collapses further. It shrinks past the neutron star stage. It compresses beyond even that impossible density, and it becomes a black hole. Only lighter cores with less than 3 solar masses, can stop at the neutron star stage. They compress to nuclear density, and then they hold. They resist. They become neutron stars instead of black holes. This is called the Tolman-Oppenheimer-Fokoff limit, a boundary predicted by physics, a line drawn by the fundamental forces of the universe. Above this mass, gravity wins completely. Nothing can resist. The core collapses to a singularity. Space and time themselves are torn apart. Below this mass, quantum mechanics wins. Degeneracy pressure holds. The star stabilizes as a neutron star. It's a delicate balance. The fate of a stellar core, decided by whether it weighs slightly more or slightly less than 3 suns. The universe is full of such thresholds, boundaries where one outcome shifts to another, where stability gives way to collapse, where structure yields to chaos. But tonight, here in this moment, you are on the stable side. You are held up, supported. The quantum pressure of your atoms, the electromagnetic forces holding your molecules together, they are more than sufficient. You will not collapse. You can rest. You can let go. The boundary is far away. You are safe on this side of it. When a neutron star is first born, in the violent moment of supernova, it is unimaginably hot. Surface temperatures can reach 1 million Kelvin, or more, much more. To put that in perspective, the surface of our Sun is about 6,000 Kelvin. The core of the Sun, where fusion occurs, is about 15 million Kelvin. A newborn neutron star surface, the outside, can rival the Sun's core. At these temperatures, atoms cannot exist. Electrons are stripped away. Matter exists as a plasma, a soup of charged particles. Everything is ionized. Everything glows. But this heat does not last. The neutron star cools rapidly. Within years, just years, the surface temperature drops from millions of Kelvin down to still millions of Kelvin, but less. Cooler. How does it cool so quickly? Through neutrinos. Remember those ghost particles we discussed? They stream out of the hot core. They carry energy away. They cool the neutron star from the inside out. Unlike normal stars, which cool primarily by radiating light from their surfaces, young neutron stars cool mainly through neutrino emission. The neutrinos escape from deep within. They don't interact with the overlying layers. They simply leave, taking heat with them. It's a rapid process. Efficient. Within 1 million years, a neutron star that was born at 1 billion Kelvin internally might cool to 1 million Kelvin at the surface. And then the cooling slows. The neutrino emission decreases. The neutron star settles into a long, slow thermal decline that will continue for billions of years. Old neutron stars. Ancient ones born when the universe was young might have surface temperatures of only a few 100,000 Kelvin, still hot enough to glow faintly in X-rays, but cool by neutron star standards. Everything cools. Everything releases its heat into the void, including you. As you lie here, your body radiates heat. Infrared light streaming off your skin, warming the air around you. A gentle thermal glow. Your core temperature is dropping slightly as you relax, as your metabolism slows for sleep, as your body prepares for rest. This is natural, normal. Cooling is not something to fear. It's a sign of equilibrium, of balance, of peace. Let the heat drain away. Let your temperature settle. Cool and rest. Inside a young neutron star, in the hot, dense core, matter undergoes strange transformations. Neutrons can convert into protons. A neutron, through a process called beta decay, becomes a proton, an electron, and a neutrino. But the reverse can happen too. A proton, capturing an electron, becomes a neutron and releases a neutrino, back and forth. Neutrons to protons, protons to neutrons. A continuous cycle of transformation. Each time this happens, a neutrino is released, and each neutrino carries away energy, heat, thermal motion. This process is called the Urca process, named oddly after casino in Rio de Janeiro. The physicists who discovered it joked that energy disappears from the neutron star core the way money disappears at the Urca casino. The Urca process is incredibly efficient at cooling. In a young neutron star, where temperatures in the core might reach billions of Kelvin, Urca cooling dominates. Neutrinos stream out by the trillion every second. The temperature plummets. Within days, the core cools from perhaps 10 billion Kelvin to a few billion. Within years, down to hundreds of millions. The cooling is exponential, dramatic, but as the temperature drops, the Urca process becomes less efficient. Fewer reactions occur. Fewer neutrinos escape. The cooling slows. Eventually, after perhaps 10,000 years, the neutron star is cooled enough that the Urca process is negligible. Other cooling mechanisms take over. The long, slow thermal evolution begins. It's a transformation, a phase transition, from violent heat to slow coolness, from chaos to order. The neutron star doesn't resist this change. It simply cools, releasing energy into the cosmos, settling into a stable state. You too are cooling. Your thoughts, once racing, are slowing. The mental energy, the activity, is releasing into the darkness, into sleep. Let it go. Let the Urca process of your mind carry away the heat of worry. Cool into stillness. After the initial neutrino cooling phase, after the Urca process is slowed, the neutron star continues to cool. But now, it cools primarily through photon emission. Through light, the hot surface radiates. X-rays stream into space. Ultraviolet light, visible light for the very hottest surfaces. This thermal radiation carries energy away, but this process is slow, much slower than neutrino cooling. The time scale for this photon-dominated cooling is called the Kelvin-Helmholtz time. For a neutron star, it's on the order of 100,000 years. 100,000 years. That's how long it takes for the surface temperature to drop from about 1 million Kelvin, where it settles after the neutrino phase, down to still pretty hot, a few 100,000 Kelvin. 100,000 years is a long time by human standards. It's longer than recorded history, longer than agriculture, longer than any human civilization. But for a neutron star, it's just a phase, a stage of cooling. After that 100,000 years, the neutron star will continue to cool for billions of years more, gradually fading, growing dimmer, approaching the background temperature of space, but never quite reaching it. Even the oldest neutron stars, born when the universe was young, still retain some residual heat. They still glow faintly. They haven't had time to cool completely. The universe itself is only about 14 billion years old. That's not long enough for a neutron star to reach thermal equilibrium with space. Everything in the cosmos is still young, still warm, still carrying the heat of creation, including Earth, including the sun, including you. Your body, formed from elements created in stars, carries warmth, the chemical energy stored in your cells, the metabolic heat of life. That warmth will last your lifetime. Steady, reliable, a gentle glow. Rest in that warmth. Let it surround you. You have time. So much time. There's no rush to cool completely. What is a neutron star made of? What fills that impossibly dense sphere? Mostly, as the name suggests, neutrons at the surface and in the outer layers. There are still some atomic nuclei, iron, nickel, heavy elements crushed into a lattice. But even here, the atoms are distorted, squeezed, not quite normal. Deeper down, in the inner crust and core, the extreme gravity crushes atoms completely. Electrons are pushed into nuclei. Protons and electrons combine into neutrons. What's left is a neutron soup, a fluid, or perhaps a superfluid, of neutrons packed together almost touching. Neutron to neutron to neutron, a sea of them. But it's not pure. There are still some protons. Perhaps 10% of the particles in the core are protons, and there must be electrons to balance the charge. These particles swim through the neutron fluid. At the very center, in the deep core where density is highest, conditions are so extreme that we're not entirely sure what exists. Possible exotic matter, quark matter, where neutrons themselves break down into their constituent quarks. Strange quark matter, color superconducting phases, states of matter that cannot exist anywhere else in the universe. Or perhaps the core is just more neutron fluid. We don't know. The physics of matter at these densities is uncertain. We can model it, predict it, but we can't test it in a laboratory. The neutron star guards its secrets. We can observe from outside, measure its mass, its radius, its cooling rate, but we cannot see within. There's a mystery at the heart of every neutron star, a question mark in the core. The universe is full of such mysteries, things we can infer but not observe, truths that remain hidden. And that's all right. Not everything must be known. Not everything must be understood. Some things can remain mysterious, peaceful in their unknowability. Rest now. Let some thoughts remain unfinished, some questions unanswered. You don't need to know everything. What holds a neutron star up? What prevents it from collapsing under its own enormous gravity? The answer is quantum mechanics, specifically neutron degeneracy pressure. Neutron, like electrons and protons, are fermions, particles that obey the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state at the same time. In a white dwarf star, it's electron degeneracy pressure that provides support. Electrons are squeezed together until they're all in the lowest available energy states. Squeeze harder, and the electrons resist. They must move faster, occupy higher energy states. This creates pressure. In a neutron star, the density is so high that electron degeneracy isn't enough. The electrons have been combined with protons to form neutrons. And now, it's the neutrons that provide the support. Neutrons are packed together. Each one occupies a quantum state. Push them closer, and they resist. The Pauli exclusion principle forbids further compression. The neutrons must move faster. They generate enormous pressure. This pressure is not thermal. It's not heat. A neutron star could be cooled to absolute zero. Theoretically, and the degeneracy pressure would remain. It's a quantum effect, a fundamental property of matter at these densities. The pressure increases rapidly with density. Compress a neutron star slightly, and the resistance increases dramatically. This creates a stable equilibrium. Gravity compresses. Degeneracy pressure resists. Balance is achieved. For neutron stars up to about 2 solar masses, this balance holds. The neutron degeneracy pressure is sufficient. But remember that limit we discussed? Around 3 solar masses, degeneracy pressure can no longer compete. Gravity wins. Collapse continues. For now, for stable neutron stars, the quantum mechanical resistance is enough. The star holds. It endures, just as you are held. supported. The electromagnetic forces between atoms in your mattress resist your weight. Quantum mechanics, at a much less extreme scale, keeps you from sinking through. You are supported, held up, safe. Rest in that support. Let it hold you as we journey deeper into the neutron star, down through the outer crust and into the inner regions. We encounter a strange phenomenon. The nuclei in the crust, iron, nickel, and heavier elements, become increasingly neutron-rich as density increases. Normally, an atomic nucleus has a balance of protons and neutrons. Too many neutrons, and the nucleus becomes unstable. It decays. A neutron converts to a proton and ejects an electron. But in the neutron star crust, gravity is so strong that unstable nuclei are forced to remain. The electrons cannot escape. The density is too high. As we go deeper, the nuclei pack more and more neutrons. They become grotesquely neutron-heavy. And then, at a certain depth, about 1 kilometer below the surface, something remarkable happens. The nuclei become so neutron-rich that they can't hold all their neutrons anymore. The neutrons begin to drip out. This is called the neutron drip line. Below this line, nuclei sit in a sea of free neutrons. The neutrons that have dripped out form a fluid, a liquid, surrounding the nuclei. This fluid carries electrical current. It conducts heat. It takes over much of the job of supporting the star's structure. Deeper still, the nuclei themselves begin to dissolve. They merge into the neutron fluid. The boundary between nucleus and free neutron becomes blurred. Eventually, in the core, there are no nuclei left, just a soup of neutrons with a few protons and electrons mixed in. The neutron drip marks a phase transition, a change in the state of matter. Above it, matter is recognizable as nuclei. Below it, matter becomes something stranger. Transitions like this happen throughout nature. Water freezes into ice. Water boils into steam. Phase boundaries where the character of matter changes. You too are approaching a transition. From wakefulness to sleep. A phase change in consciousness. Let it happen. Let the boundary approach. Let yourself drift into sleep at the moment of neutron drip. When free neutrons first begin to permeate the crust, an interesting balance exists. The pressure, the force that holds a star up against gravity, comes from multiple sources. Above the neutron drip line, most of the pressure comes from electrons. These degenerate electrons, squeezed by the Pauli exclusion principle, provide most of the support. But at the drip line itself, as neutrons begin to leak out of nuclei, the free neutrons start contributing to the pressure too. At this transition point, the electron pressure and neutron pressure are roughly comparable. Balanced, equal partners in holding up the star. But as density increases further, as we go deeper, the neutron pressure quickly becomes dominant. Why? Because there are more neutrons. And because neutrons being much heavier than electrons, carry more momentum at a given speed. They generate more pressure. Soon, just a little deeper than the drip line, the neutrons are doing most of the work. The electrons are still there, still contributing, but the neutrons dominate. And deeper still, when the nuclei fully dissolve, neutron degeneracy pressure is essentially the only thing holding the star up. This transition is smooth, gradual. There's no sharp boundary, just a steady shift from electron-supported matter to neutron-supported matter. It's like a relay race. Electrons carry the pressure load for the outer layers. Then they hand off to neutrons. The neutrons take over. They carry the load for the core. Everything works together. Each layer contributes. Each region plays its part. Your body is like this too. Multiple systems working together. Your heart pumps blood. Your lungs breathe, your brain coordinates, each system supporting the others. And now, those systems are shifting into rest mode, transitioning, handing off from active wakefulness to sleep. Let the transition happen. Let each system settle. Let sleep take over. In the deepest parts of the neutron star's crust, just above the core, matter takes on bizarre shapes. The density here is enormous, close to nuclear density. Nuclei are packed so tightly that they're nearly touching. And under these conditions, they begin to deform. Instead of round spheres, nuclei stretch into rods, cylinders, long strands of nuclear matter aligned in parallel. Push deeper, increase the density further, and the rods connect. They form sheets, flat planes of nuclear matter layered like lasagna. This is why physicists call these structures nuclear pasta. There are different phases, different shapes. Spaghetti, long rods. Lasagna, flat sheets. Anti-spaghetti, cylindrical holes in a continuous medium. Anti-lasagna, flat voids. These pasta structures are stronger than steel, stronger than diamond. They're the strongest material in the universe. And yet, under the neutron star's immense gravity, they fold, they bend, they fracture. When the crust suddenly cracks, when the pasta structures shear under accumulated stress, the event is called a starquake. The entire star rings like a bell. Energy is released. Sometimes, for magnetars, this energy powers a giant flare of X-rays and gamma rays. But most of the time, the pasta just sits there, stable, enduring, holding up the overlying layers, supporting the star. These structures exist nowhere else. You cannot make nuclear pasta in a laboratory. The densities required are too high. The pressures too extreme. They exist only in neutron star crusts, a unique phase of matter, strange, beautiful in its strangeness. The universe creates things that defy imagination, structures our minds struggle to visualize, and yet they're real. They're there, spinning in the darkness. Let your mind struggle less now. Let visualization fade. Let the strange become the familiar. Let pasta be pasta, and let sleep be sleep. The neutron star's solid crust, that layer of exotic nuclei and nuclear pasta, is not very thick, just 1 kilometer. 1 kilometer, about half a mile, the distance you might walk in 10 or 15 minutes. That's all. That's the entire thickness of the crust, from the surface, where matter is still recognizable as atoms, down to core, where matter becomes pure neutron fluid, is only 1 kilometer. And yet, this thin crust supports immense shear stresses. Shear stress is the force that tries to slide layers past each other. Like when you push on the top of a deck of cards and the bottom stays fixed. The cards in the middle experience shear. In the neutron star crust, the inner layers rotate at one speed, the outer layers at another. This differential rotation creates shear. The pasta structures strain under the stress. Eventually, they fracture. The crust cracks. A starquake occurs. For magnetars, neutron stars with ultra-strong magnetic fields, these starquakes can be catastrophic. The sudden release of energy triggers a magnetic flare. Gamma rays and X-rays burst outward. For a fraction of a second, the magnetar outshines the entire galaxy. But for normal neutron stars, starquakes are quieter, gentler, a subtle adjustment, a release of strain. The star settles into a slightly new configuration and continues spinning. 1 kilometer, such a thin shell, and yet strong enough to support a neutron star, strong enough to endure for millions of years between major fractures. You too have a shell, your skin, your skeleton, the structure that holds you together. It's thin compared to your full volume, but it's strong, sufficient. Rest in that strength. You are held together. You will not fracture. You can relax. The crust of your consciousness is thinning now, the boundary between wake and sleep growing permeable. Soon it will crack, and you will slip through into sleep. Let it happen. Let the starquake come. Let yourself break through into rest. Deep within the neutron star's core, in that region of pure neutron fluid, something extraordinary happens. The neutrons become a superfluid. A superfluid is matter in a special state, a quantum state, at low temperatures, below a critical threshold. Certain fluids lose all resistance to flow. All friction disappears. Pour normal water through a pipe, and friction with the walls slows it down. Eventually it stops. Pour superfluid to the same pipe, and it flows forever, without slowing, without stopping. It has zero viscosity. This happens in the neutron star core because of pairing. Neutrons, despite being electrically neutral, attract each other weakly through nuclear forces. At low enough temperatures, they form pairs. These pairs behave as bosons. And bosons, unlike fermions, can all occupy the same quantum state. When they do, they form a superfluid. The neutron superfluid flows without resistance. Vortices form in it, tiny whirlpools of rotating superfluid, and these vortices are quantized. Each vortex has exactly the same circulation, exactly the same angular momentum. This superfluidity explains several mysteries of neutron star behavior. For instance, glitches. Sometimes a pulsar's rotation rate suddenly increases, just slightly. The star spins a tiny bit faster for a moment, then it slowly relaxes back. These glitches are thought to be caused by the superfluid core. The core, rotating frictionlessly, doesn't slow down when the crust slows. A differential rotation builds up. Eventually, vortices in the superfluid unpin from the crust. Angular momentum transfers suddenly. The crust spins up. A glitch. It's a quantum phenomenon, a macroscopic manifestation of quantum mechanics. An entire stellar core, containing more mass than our sun, behaving as a single quantum fluid. The superfluid flows in darkness, unobserved, frictionless, eternal, like your thoughts now, flowing without resistance, without effort, drifting from one idea to the next without friction. Let that flow continue. Let your mind become superfluid. Let all resistance drain away. Flow into sleep. What happens if exotic particles form in the neutron star core? At extremely high densities, neutrons might not be the only particles present. Hyperons, strange particles containing strange quarks, might appear. Lambda baryons, sigma baryons, Xi baryons. These particles are unstable under normal conditions. They decay in fractions of a second. But in the neutron star core, the high density stabilizes them. The problem is hyperons soften the equation of state. They make matter more compressible. This reduces the pressure at a given density. And reduced pressure means the star might not be able to support as much mass. There's a phenomenon called the hyperon puzzle. Models that include hyperons predict maximum masses around 1.4 solar masses. But we observe neutron stars with 2 solar masses. Even more, how can this be? One possibility is that hyperons create an island of stability at certain densities. The presence of hyperons actually prevents further collapse. They stabilize the core. The star settles at a mass around 1.4 solar masses and remains there, stable, unable to accrete more matter without collapsing. This would explain why many neutron stars cluster around this mass. They've reached the island. They're stable there. But it's just a theory. We don't know for certain. The interior of a neutron star remains hidden from us. We can only model, predict, infer. The universe has islands of stability throughout, regions of parameter space where things balance, where forces align, where objects endure. Earth is on an island of stability. In the habitable zone around the sun, not too hot, not too cold, liquid water can exist. Life can flourish. You are on an island of stability too. Your body temperature, your heart rate, your breathing, all balanced in a narrow range where life functions well. Rest on that island. You don't need to wander. You don't need to explore. You can simply remain stable, at peace. What if we go even deeper? What if the density at the very center of the neutron star is so high that even neutrons break down? Neutrons are not elementary particles. They're composite, made of quarks. A neutron contains 3 quarks, 2 down quarks and 1 up quark. These quarks are bound together by the strong nuclear force. They're confined. Under normal conditions, you cannot separate them, but at extreme density, at pressures beyond what neutron degeneracy can support, the boundaries between neutrons might dissolve. The quarks would become deconfined, free. They would form a quark-gluon plasma, or, at lower temperatures, perhaps a quark liquid. This matter would be a soup of up quarks and down quarks, and possibly strange quarks. Strange quarks are heavier than up and down quarks. They don't appear in normal matter, but at high density, they become energetically favorable. The core would be strange quark matter, a fluid of quarks, not bound into protons or neutrons, just free quarks, swimming in a sea of gluons. Some theorists have suggested that strange quark matter might be the true ground state of matter, more stable even than atomic nuclei. If this is true, then neutron stars might gradually convert to strange stars, stars made entirely of quark matter. But we don't know. We've never observed quark matter directly. We can't create it in laboratories at the densities required. The neutron star core might contain it, or it might not. The pressure might be too low, the temperature too high, the conditions not quite right. It remains a mystery, a question mark at the heart of the densest objects in the universe. Some questions don't have answers yet. Some mysteries remain unsolved. And that's all right. Not everything must be known tonight. Let the quarks remain mysterious. Let the core remain hidden. Let your mind release the need to understand. Rest in uncertainty. Rest in the unknown. Physicists would very much like to know the equation of state of neutron star matter. The equation of state is a relationship. It tells you, given a certain density, what the pressure will be, and given a certain pressure, what the density will be. For normal matter, like the air around you or the water in the ocean, we know the equation of state quite well. We can predict how gases compress, how liquids flow. But for neutron star matter at nuclear density and beyond, we don't know the equation of state with certainty. Is the matter stiff? Does it resist compression strongly? Or is it soft? Does it compress easily? A stiff equation of state allows larger neutron stars, higher maximum masses, thicker crusts. A soft equation of state produces smaller stars, lower maximum masses, thinner crusts. Different assumptions about the composition, neutrons only or hyperons or quark matter, produced different equations of state. And here's the problem. Observations from outside the star can't distinguish between them. We can measure a neutron star's mass. We can estimate its radius. We can observe its cooling rate. But multiple equations of state can produce the same observable properties. It's like trying to guess what's inside a lockbox by weighing it and shaking it. You can learn something, but you can't know for certain. This is one of the great unsolved problems in astrophysics. What is the equation of state of ultra-dense matter? Gravitational wave observations are helping. When neutron stars merge, the way they deform tells us about their stiffness. We're narrowing down the possibilities. But a definitive answer? Not yet. The mystery remains. Some mysteries take decades to solve. Some take centuries. Some, perhaps, are never fully solved, only constrained, narrowed, made less uncertain. That's okay. Progress doesn't require complete knowledge, just gradual understanding, slow refinement. Like sleep, it doesn't come all at once. It arrives gradually, uncertain at first, but deepening, narrowing down, until suddenly you're asleep. Let that process continue. Let understanding fade. Let certainty dissolve. On August 17th, 2017, two neutron stars collided. They had been orbiting each other for millions of years, gradually spiraling inward, drawing closer, their orbits decaying as they radiated gravitational waves. And finally they touched. They merged. They tore each other apart in a fraction of a second. The collision produced gravitational waves that rippled across the universe, distortions in space-time itself, stretching and squeezing space as they passed. On Earth, two gravitational wave detectors, LIGO in the United States and Virgo in Europe, detected those waves. For 100 seconds, they recorded the signal as the neutron stars spiraled inward. The signal was called GW170817, the first gravitational wave detection from merging neutron stars. And from that signal, astronomers learned something profound. The way the neutron stars deformed as they approached each other, the way tidal forces stretched them, depended on their internal structure, on their equation of state. A stiff neutron star resists tidal deformation. It stays nearly spherical, even as gravity tries to stretch it. A soft neutron star deforms more easily. It becomes elongated, football-shaped. The gravitational wave signal encoded this information, and when astronomers analyzed it, they found constraints. Neutron star radii must be between 11 and 13 kilometers. That's it. Not too small, not too large. Somewhere in that range. This ruled out some equation of state models. The very stiffest models, which predicted radii of 15 or 16 kilometers, were excluded, and the very softest models, predicting radii below 10 kilometers, were also excluded. The range narrowed, uncertainty decreased. One collision, 100 seconds of data. and our understanding improved. Sometimes a brief moment of observation reveals more than years of theory, a flash of insight, a sudden constraint. Your mind is narrowing now too, the range of thoughts reducing, focusing, constraining down toward a single state. Sleep, let the range narrow. Let possibilities collapse. Let only sleep remain. Among the neutron stars we've observed, one stands out as particularly small. PSR J0931-1902, a pulsar discovered by its radio emissions. Careful observations of its orbit, its gravitational effects on a companion star, allowed astronomers to measure its mass and radius. The radius is under 13 kilometers, probably closer to 12, maybe even 11. This is at the lower end of what theory predicts, near the minimum stable size for a neutron star. Why is there a minimum size? Because neutron degeneracy pressure increases with density. Compress a neutron star too much, make it too small, and the degeneracy pressure becomes enormous. It pushes back, prevents further compression. There's an equilibrium, a balance. And for neutron stars around 1.4 solar masses, that balance occurs at a radius of about 11 to 12 kilometers. Go much smaller, and you'd need less mass. But less mass means less gravity to compress the star in the first place. So there's a minimum, a floor, below which neutron stars don't exist. PSR J0931-1902 is near that floor. Small, dense, compact. It challenges our models, makes us refine our equations, improve our understanding. Every extreme case teaches us something. Every object at the edge of possibility reveals the boundaries of physics. You too have boundaries, limits, a minimum and maximum heart rate, a temperature range you can tolerate, a range of sleep you need. You're approaching one of those boundaries now, the edge between wake and sleep, the minimum consciousness required to remain awake. Soon, you'll cross that boundary, slip below it, into sleep. Let it happen. Let yourself approach the minimum, and then let yourself fall below it. When astronomers catalog compact objects, neutron stars, and black holes, they notice something strange. There's a gap. Below about 2.5 solar masses, we find neutron stars, pulsars, magnetars, many of them. Above about 5 solar masses, we find black holes. Stellar mass black holes form from the collapse of massive stars. But between 2.5 and 5 solar masses, almost nothing. There are a few candidates, a couple of uncertain detections, but no confirmed objects in this range. Why? It's called the mass gap, and it's a puzzle. One possibility is that the transition from neutron star to black hole is sharp. Once a collapsing core exceeds about 2 to 3 solar masses, it doesn't stop at the neutron star stage. Degeneracy pressure fails. The core plunges straight through to black hole formation. No intermediate stage. no objects in the gap. Another possibility is that supernova explosions are very efficient. They either leave behind neutron stars, light cores that stop at 1 to 2 solar masses, or they completely disrupt the star. No remnant at all. Heavy cores above 3 solar masses might be rare, or they might form black holes directly. No neutron star phase. The gap might be telling us something fundamental about supernova physics, about the explosion mechanism, about which stars leave remnants and which don't. Or it might be an observational bias. Maybe objects in the mass gap are harder to detect, quiet, not pulsing, not accreting matter, just sitting there in the dark, invisible to our telescopes. We don't know yet. The puzzle remains unsolved. Gaps in knowledge, holes in our understanding. They're everywhere, in every field, every science. But gaps aren't failures. They're opportunities, places where new discoveries wait. Your mind has gaps too, forgotten memories, dreams you don't recall, thoughts that slip away before you can grasp them. That's normal, natural. The mind doesn't need to hold everything. Let the gaps remain. Let some things fall through into the mass gap of sleep, lost, unretrieved. It's okay. Not everything needs to be remembered. Neutron stars spin, and many of them spin fast, very fast. When a massive star collapses, when its core shrinks from thousands of kilometers across down to 10 or 20 kilometers, angular momentum is conserved. Angular momentum is the rotational equivalent of linear momentum. An object in motion stays in motion, and an object spinning stays spinning. The star's core was rotating slowly before collapse, perhaps once every few days, or once per week. But when it collapses, when the radius shrinks by a factor of 1,000 or more, the rotation rate increases, like a figure skater pulling in their arms. They spin faster, much faster. The neutron star is born spinning rapidly, perhaps once per second, perhaps faster. And some neutron stars, pulsars that have been spun up by accreting matter from a companion, spin even faster, hundreds of times per second. The fastest known is PSR J1748-2446 AD, a pulsar in a globular cluster. It rotates 716 times per second, 716 times every second. The surface of this neutron star at its equator is moving at 24% of the speed of light, nearly a quarter of the ultimate speed limit, whirling, spinning, blurring. At that speed, relativistic effects become important. Time dilation, length contraction. The star is flattened slightly by centrifugal force, distorted from a perfect sphere, but it holds together. Gravity is strong enough to keep the star from flying apart. 716 rotations per second for millions of years. Steady, reliable. These pulsars are the most accurate clocks in the universe, more stable than atomic clocks on Earth. Astronomers use them to detect gravitational waves, to navigate spacecraft, to test general relativity. A spinning neutron star, a cosmic lighthouse, sweeping its beam across the galaxy with perfect regularity. Your heartbeat is a clock too, slower, much slower, but steady. As you drift towards sleep, your heart rate slows. The clock ticks more slowly. The rotation rate decreases. That's good. That's rest. Let the spinning slow. Let the rotation ease. You don't need to spin hundreds of times per second. You can slow. You can rest. Let the lighthouse beam fade. Let the pulses stretch out. Slow, slower, until sleep. Neutron stars have magnetic fields. Strong ones. Earth has a magnetic field. It's what makes a compass work, what creates the auroras. It's about half a Gauss at the surface. The sun has a stronger field, thousands of Gauss in sunspots. But neutron stars, their fields reach trillions of Gauss, a million times stronger than Earth's field. How do they get such strong fields? When the stellar core collapses, the magnetic field is compressed along with everything else. The field lines are squeezed together. The field strength increases. It's like taking a bar magnet and crushing it down to a fraction of its size. The field becomes more concentrated, more intense. For a neutron star, the field can reach 10 to the 12 Gauss, or even higher. Magnetars, a special class of neutron star, have fields up to 10 to the 15 Gauss, a quadrillion times Earth's field. These fields are strong enough to distort atoms, to make empty space birefringent, to pull iron out of your blood if you got too close. Of course, you won't get close. Neutron stars are far away. Their magnetic fields, intense as they are, don't reach us here. But the fields do affect the stars themselves. They channel particles. Electrons and positrons stream along magnetic field lines. They accelerate. They radiate. This creates beams, cones of radio waves, or X-rays, or gamma rays, shining out from the magnetic poles. As the neutron star rotates, these beams sweep across space like a lighthouse. And if one of those beams happens to sweep across Earth, we see a pulse, a pulsar. The magnetic field is what powers the emission, what makes the pulsar visible, what lets us detect neutron stars that would otherwise be invisible. Fields, invisible, permeating space, organizing, guiding, creating structure out of chaos. Your brain has fields too. Electrical fields from neural activity. Weak, but real, measurable. As you sleep, those fields change. The patterns shift. High-frequency activity decreases. Slow waves emerge. Let those fields reorganize. Let the fast pulses slow. Let the magnetic sweep of consciousness wind down. The lighthouse is dimming. The beam is fading. Soon darkness. Pulsars don't spin at the same rate forever. They slow down, very slowly, gradually, but measurably. Why do they slow? Because they're radiating energy. The spinning magnetic field, rotating with the star, acts like a magnetic dipole, and a rotating magnetic dipole radiates electromagnetic waves. This is called magnetic dipole radiation. The energy for this radiation comes from the pulsar's rotation. As the pulsar radiates, it loses rotational energy. It slows down. The rate of energy loss, the luminosity, is proportional to a specific combination of parameters. The spin-down luminosity depends on the period p and the period derivative p dot. That is, how fast the period is increasing. The formula is L is proportional to p dot divided by p cubed. What does this mean? Pulsars with short periods lose energy faster. A pulsar spinning 100 times per second loses more energy than one spinning once per second. And pulsars that are slowing down rapidly, large p dot, also lose energy faster. Young pulsars, freshly born, have short periods and rapid spin down. They're very luminous. They shine brightly in radio waves. In X-rays, old pulsars, millions of years old, have slowed considerably. Their periods are longer. Their spin down is slower. They're faint, dim. Eventually, a pulsar slows so much that it stops emitting detectable radiation. It becomes a dead neutron star. Still there, still spinning, but invisible, silent. The spin down is inexorable, slow, but unstoppable. Every rotation, energy is lost. Every pulse, a tiny fraction slower than the last. Over millions of years, the pulsar dims, fades, falls silent. Everything slows eventually. Everything loses energy to its surroundings. This is entropy. The second law of thermodynamics. Energy disperses. Order fades. But slowly, so slowly, your energy is dispersing too. Radiating away as heat. As infrared light, your metabolic rate slowing. Your activity decreasing, you're spinning down, pulsing more slowly, dimming. This is sleep, this is rest. This is the natural state of a tired mind. Let the spin down continue. Let the period lengthen. Let the pulses fade. Soon silence, soon stillness, soon sleep. In the intense magnetic fields near a neutron star, something remarkable happens to light. Gamma rays, high-energy photons, can transform into matter. This sounds like science fiction. Energy becoming mass. But it's real. It's a consequence of Einstein's famous equation. E equals mc squared. Energy and mass are equivalent. When a gamma-ray photon has enough energy, above 100 million electron volts, and when it passes through a strong magnetic field, it can split. It becomes two particles, an electron and a positron. A positron is the antimatter version of an electron. Same mass, opposite charge. The two particles spiral away from each other along magnetic field lines. This is called pair production. In the magnetosphere of a neutron star, the region around the star where the magnetic field dominates. Pair production happens constantly. Gamma rays stream out from the star's surface or from accelerated particles. They interact with the magnetic field. Pairs are created. These electrons and positrons contribute to the pulsar's emission. They accelerate along field lines. They radiate. They create the beams of radio waves and X-rays that we detect. The magnetosphere becomes filled with particles, a plasma of electrons and positrons, swirling, spiraling, radiating. It's a violent environment, energetic, chaotic, but also, in a strange way, creative. Light becoming matter, energy crystallizing into particles, the void filling with substance, creation from nothing, or not nothing, from energy, from the rotation of the star, from the magnetic field. Everything comes from something else. Energy transforms, mass converts. Nothing is truly created, nothing truly destroyed, just transformed. Your thoughts are transforming now, from wakefulness to drowsiness, from activity to rest, not disappearing, just changing form. Let the transformation continue. Let energy become stillness. Let activity become sleep. The pair production we just described can become unstable in very strong magnetic fields, especially near magnetars. The rate of pair production can be enormous. Vast numbers of electron-positron pairs are created. These pairs carry electrical charge. They conduct electricity. And a conducting plasma can short-circuit the magnetic field. Imagine trying to maintain a magnetic field through a perfect conductor. It can't be done. The currents induced in the conductor create their own magnetic field that cancels the original in the magnetosphere. If too many pairs are created, the plasma becomes so conductive that it screens the magnetic field. The field can't penetrate. It's short-circuited. This instability might trigger pulsar radio emission. When the field is screened, accelerating voltages collapse. Particle acceleration stops. The emission turns off. But then, without acceleration, no more pairs are created. The plasma drifts away or annihilates. The field reasserts itself, and the cycle begins again. Acceleration, pair production, instability, shutdown, recovery, repeat. This might happen billions of times per second, creating the coherent radio emission we detect from pulsars. It's an instability, a feedback loop. The system oscillates between two states, on and off, active and quiescent. Unstable systems can be beautiful. They create patterns, rhythms, oscillations. Your breathing is like this. Breathe in, breathe out, an oscillation, a cycle. As you drift towards sleep, the rhythm slows, the oscillation lengthens, becomes smoother, more regular. Let the instability fade. Let the oscillation deepen. Let the rhythm carry you in and out, into sleep. The magnetic field of a neutron star doesn't necessarily align with its rotation axis. For Earth, the magnetic poles and geographic poles are close. They're misaligned by about 11 degrees. This is why compasses don't point exactly north. For neutron stars, the misalignment can be much larger. The magnetic axis and the rotation axis can be tilted relative to each other by 10 degrees, or 30, or 60, or 90 degrees. 90 degrees is called an orthogonal rotator. The magnetic poles lie on the star's equator. As the star spins, the magnetic field sweeps through the largest possible angle. Why does this misalignment occur? Probably because of how the star was born. The magnetic field in the original star's core wasn't necessarily aligned with the rotation axis. When the core collapsed, the misalignment was preserved. Or perhaps the magnetic field reorganizes itself after birth, drifting, realigning, settling into a configuration that's not quite symmetric. Whatever the cause, the misalignment is crucial for pulsar emission. If the magnetic axis were perfectly aligned with the rotation axis, the magnetic field would spin like a spinning top, symmetric, not changing from our perspective. We wouldn't see pulses. But with misalignment, the magnetic field wobbles. The beams sweep across space. And if Earth happens to lie in the path, we see a pulse, then another, regular, periodic, lighthouse-like, orthogonal rotators with 90-degree misalignment sweep the largest volume of space. Their beams are more likely to hit Earth. They appear brighter. Smaller misalignments, 10 or 20 degrees, produce narrower sweeps, fainter pulses. Alignment matters. Geometry matters. The same neutron star, viewed from different angles, appears completely different. Your perspective matters too. How you see things. How you orient yourself. But now, orientation is fading, up and down blending, the room tilting, spinning, misaligning. Let the alignment drift. Let geometry dissolve. Let perspective fade. Soon, there'll be no angle, no axis, just sleep. The beams emitted by pulsars are not wide. They're narrow, very narrow. A typical pulsar beam is a cone, 5 to 10 degrees wide, like a flashlight beam or a spotlight from a neutron star's perspective. This beam sweeps across space as the star rotates, cutting through the void, illuminating nothing, unless by chance Earth happens to lie in the path. If Earth is within that 5 to 10 degree cone for even a moment, we see a pulse, a flash of radio waves, or X-rays. Then the beam sweeps past. The sky goes dark. We wait, and then one rotation later, the beam returns. Another pulse. This narrowness has important implications. It means that most neutron stars are invisible to us. Their beams point elsewhere. We're not in the cone. We see nothing. We can infer that they're there. We might see the supernova remnant, the expanding shell of gas from the explosion. We can calculate that a neutron star should be at the center, but we don't see it. The lighthouse beam is aimed away from us. Only when the geometry is just right, when the spin axis, the magnetic axis, and Earth all align properly, only then do we see the pulsar. This is why pulsars are relatively rare. Not because neutron stars are rare, but because detection requires this precise alignment. Most neutron stars are dark to us, silent, spinning in the void, shining their beams into empty space, unobserved, unknown. There's something peaceful about that. Objects existing beyond our perception. Real, present, but hidden. Your consciousness is narrowing now too. The beam of awareness becoming focused, directed, narrow. Soon, it will point away from wakefulness, aim towards sleep, and the waking world will go dark. Let the beam sweep away. Let awareness narrow. Let perception fade. Let's think about this more carefully. Let's do the geometry. A pulsar beam is about 5 to 10 degrees wide. Let's say 8 degrees on average. The beam sweeps around as the star rotates. It traces a cone in space. If the magnetic axis is aligned with the rotation axis, the cone degenerates to a line. No sweep. We don't see it. If the magnetic axis is misaligned, the cone opens up. The beam sweeps across a band in space. Now, Earth is in a random direction relative to pulsar. The pulsar's orientation is random. What's the probability that Earth lies within the beam sweep? It depends on the geometry. But roughly, for typical misalignment angles, it's about 1%. 1%. That means for every 100 neutron stars, we only see one as a pulsar. The other 99 are there, spinning, emitting, but their beams don't hit us. This explains the detection gap. We know from supernova rates that neutron stars should be common. The Milky Way should contain hundreds of millions of them. But we've only detected a few thousand pulsars. Where are the rest? They're there, just invisible. Their beacons pointed elsewhere. It's a reminder of how limited our perspective is. We see only what is aimed at us, what aligns with our line of sight. The universe is much larger, much more full than what we can observe. Invisible objects, hidden stars, dark neutron stars spinning in the void. They don't care that we can't see them. They don't need our observation to exist. You don't need to be observed either. You can exist here, alone in the dark, unseen. Let observation fade. Let the beam sweep away. Let yourself become invisible, into the dark, into sleep. The lighthouse analogy is so perfect, so apt, that it's worth spending a moment with. A lighthouse sits on a rocky shore. At night, it shines a beam of light, rotating, sweeping across the ocean, warning ships of danger. If you're a sailor far out at sea, you see the flash, then darkness, then another flash, regular, periodic, The lighthouse doesn't shine everywhere at once, just in a narrow beam. Most of the ocean is dark. Only the narrow path of the beam is illuminated. A pulsar is the same. It's a cosmic lighthouse, spinning in space, sweeping its radio beam across the galaxy. If Earth is in the path, we see a pulse, then darkness, then another pulse, regular, periodic. The first astronomers to see this signal in 1967 were amazed. A signal from space, repeating every 1.337 seconds. Precise, unwavering. It seemed artificial, deliberate. Could it be aliens? They labeled it LGM-1. Little green men 1. But as more signals were found with different periods in different parts of the sky, it became clear this was natural, not a message, just a spinning neutron star, a lighthouse, many neutron stars, invisible to us, their beams aimed elsewhere. But the few we can see, the few whose beams sweep past Earth, they've taught us so much about extreme physics, about general relativity, about the universe. Lighthouses guide ships to safety. Pulsars guide our understanding the truth. You are safe here, guided by the rhythm of your breath, the lighthouse of your heartbeat. Let the beam sweep. Let the pulse continue. Regular, steady, and let consciousness, let wakefulness drift out of the beam into the dark between pulses, into sleep. This point is worth emphasizing. It's easy to forget. When a massive star explodes, we see the supernova, a brilliant flash, brighter than a galaxy for a few weeks. The light fades. The expanding shell of gas, the supernova remnant, glows faintly. We can see it for thousands of years. At the center, probably there's a neutron star, the collapsed core, the remnant, but we might not see it. If the neutron star's magnetic poles, and thus its radiation beams, don't sweep across Earth, it's invisible. We infer that it's there. The physics predicts it. The core should have collapsed to a neutron star. It should be there. But we see nothing. No pulses. No X-ray emission. Nothing. The neutron star is there. Spinning. Hot. Radiating. But the beams point elsewhere. This happens often. Many supernova remnants have no detected pulsar at the center. Either the neutron star wasn't formed, unlikely for most cases, or it's there but invisible, hidden, unobservable, real but unseen. The universe is full of things we can't see. Dark matter, dark energy, black holes before they accrete, and neutron stars whose beams miss us. Existence doesn't require observation. You don't need to be observed to exist, to rest, to sleep. Let yourself become unobservable. Let the beams sweep away from wakefulness. Let yourself exist quietly, invisibly in sleep. When the geometry is right, when the rotation axis tilts and the magnetic beams sweep across Earth, we see regular pulses. These pulses are extraordinarily regular. more regular than any clock humans have built. Millisecond pulsars, old neutron stars spun up by accreting matter, can have periods stable to 1 part in 10 to the 15th. That's more stable than atomic clocks, more regular than the vibrations of cesium atoms. For a while, in the 1970s and 80s, pulsars defined the most accurate time standard available. Pulsar timing was more precise than atomic clocks. Eventually, our atomic clocks improved, but pulsars remain competitive. And for long-term stability, over years and decades, pulsars are still unmatched. These cosmic beacons, these lighthouses, they mark time for the galaxy. Jocelyn Bell Burnell discovered the first one in 1967. She was a graduate student working with Anthony Hewish, building a radio telescope to study quasars. The telescope was designed to detect twinkling, scintillation, radio sources that vary due to the interstellar medium. And one day, she noticed something odd, a signal, repeating every 1.337 seconds, like clockwork. At first, it seemed like interference, radio noise from Earth, but it appeared at the same point in the sky every night. It moved with the stars, not with the sun or Earth. It was cosmic. After ruling out everything else, including the possibility of alien signals, they realized this was a neutron star, spinning, pulsing, a pulsar. The discovery revolutionized astrophysics, confirmed the existence of neutron stars, opened a new window on extreme physics. And it all started with a graduate student noticing an odd signal, paying attention, investigating, small observations, careful attention. They can reveal profound truths. Your attention is fading now. Small observations becoming difficult, details blurring. That's okay. You don't need to notice everything. You don't need to pay attention. Let observation cease. Let the beacon fade. Let tension drift away. PSR be 1919 plus 21. The first pulsar, the first neutron star ever detected. It's in the constellation Vulpecula, the little fox, about 2,000 light years away. It pulses every 1.337 seconds. Regular, unwavering. When Jocelyn Bell first saw the signal, she marked it on the chart paper. Scruff. That's what she called it. An odd bit of noise. Interference, maybe. But it kept appearing. Same time every sidereal day. Locked to the stars. She told Hewish. They investigated. They ruled out satellites, aircraft, terrestrial interference, solar system effects. It was cosmic, and it was periodic, impossibly periodic. For a brief time, they genuinely considered the possibility of an alien civilization, an artificial beacon, a signal. They labeled it LGM-1, Little Green Men 1. But Jocelyn Bell found more signals, different periods, different locations. LGM-2, LGM 3. If these were alien civilizations, they were everywhere, and they were all signaling at different rates, with no apparent pattern. That seemed unlikely. The explanation that fit, that made sense, was natural. Neutron stars, predicted theoretically decades earlier, now detected, spinning, pulsing, lighthouses in the cosmic dark. Anthony Hewish won the Nobel Prize for the discovery. Jocelyn Bell did not. This was controversial. Many felt she deserved to share the prize, but she remained gracious, continued her work, became an eminent astronomer, advocated for women in science. The first detection, the first confirmation, a graduate student's careful observation. It changed everything. First steps, first observations. They lead to great things, but they start small, simple, unremarkable. Your first step into sleep, your first drift. It's happening now. Small, simple, but it will lead somewhere. Into rest, into dreams, into renewal. Let the first pulse of sleep begin. Jocelyn Bell's telescope wasn't designed to find pulsars. It was designed for something else entirely. Interplanetary scintillation. When radio waves travel through the solar system, they pass through the solar wind. Charged particles streaming out from the sun. This plasma causes the radio waves to twinkle, to scintillate, just like stars twinkle in visible light. When their light passes through Earth's atmosphere, the turbulent air bends the light, creates fluctuations, twinkling. Radio waves do the same when passing through plasma. They twinkle on timescales of seconds to minutes. Hewish and Bell were studying this effect, trying to understand the solar wind, map its structure. Their telescope was sensitive to rapid variations. It recorded data on a chart recorder, long scrolls of paper, pens tracing the signal strength. And one day, Bell noticed something that didn't fit. A signal that scintillated too regularly, too precisely. Not random twinkling, but periodic pulses. 1.337 seconds apart. It shouldn't have been there. The telescope wasn't designed for this. But there it was. Serendipity, accident, luck, or maybe careful observation. Noticing what doesn't fit, what seems odd. Bell checked the chart recordings every day. Miles of paper, looking for anomalies, for scintillation patterns. And she found the pulsar. PSR be 1919 plus 21. The first. Sometimes the tools we build for one purpose reveal something else entirely. Unexpected, profound. Sometimes paying attention to the wrong thing leads to the right discovery. Your attention is wandering now, drifting from wakefulness, noticing odd things, dream fragments, random thoughts. That's okay. Let it wander. Let attention drift to the wrong places, the unexpected places. Sleep is there, in the unexpected, in the place you weren't looking. Let yourself find it, by accident, by serendipity, by letting go. When a neutron star is first born, in the chaos of supernova explosion, it might not pulse. About 90% of young neutron stars are radio quiet initially. They're there, spinning, hot, magnetic, but they don't emit detectable radio pulses. Why not? The magnetosphere, the region around the star where the magnetic field dominates, needs time to organize, to settle, to establish the conditions necessary for particle acceleration and coherent emission. In the first hours or days after birth, the magnetosphere is chaotic, turbulent. The magnetic field is tangled. Particles are scattered. Gradually, over weeks or months, the magnetosphere adjusts. Field lines straighten. Currents establish themselves. Acceleration gaps form. And then the radio emission turns on. The pulsar activates. It begins to pulse. But until that happens, the neutron star is invisible in radio surveys. We wouldn't know it's there. We might see the supernova remnant. We might infer a neutron star should exist, but we can't detect it yet. It's sleeping, dormant, not yet fully born into observability. Eventually it wakes. The magnetosphere settles. The beams activate, and the pulsar announces itself to the galaxy. But those first weeks, those first months, it's quiet, silent, resting. You're quiet now too, silent. The magnetosphere of your mind settling, organizing. Soon, the emission will stop entirely. Consciousness will go radio quiet. Sleep will activate. Let the adjustment happen. Let the magnetosphere settle. Let silence deepen. Radio waves from pulsars don't travel in straight lines. Not exactly. As they journey through galaxy, they pass through clouds of ionized gas, the interstellar medium, regions of plasma, electrons and ions floating in the void. These charged particles affect the radio waves. They scatter them, bend them, delay them. Different frequencies are affected differently. Higher frequencies, shorter wavelengths, pass through more easily. Lower frequencies, longer wavelengths, scatter more. This creates a phenomenon called dispersion. The radio pulse, emitted as a sharp spike, spreads out as it travels. Higher frequencies arrive first. Lower frequencies arrive later. By measuring this dispersion, astronomers can calculate the distance to the pulsar. More dispersion means more intervening plasma, more distance. But dispersion has a downside. It limits detectability. If the pulse spreads out too much, if it's smeared over too long a time, it might become undetectable, lost in the noise. For distant pulsars or pulsars behind dense clouds of plasma, the scattering is so severe that we can't see them, even though they're pulsing, even though they're bright. The interstellar medium hides them from view. We can detect nearby pulsars easily, and we can detect distant pulsars if we observe at high frequencies, where scattering is less severe, but low-frequency searches at long wavelengths are limited to the local neighborhood, a few thousand light years at most. The galaxy is murky, opaque, full of scattering plasma. Many pulsars are there, pulsing faithfully, but hidden from us by the fog of space. Your vision is scattering too, blurring, the sharp edges of perception spreading out, smearing, high frequencies of thought arriving weakly, low frequencies dominant, slow, scattered. Let the scattering continue. Let vision blur. Let sharpness soften into fog. Neutron stars don't just emit in one part of the electromagnetic spectrum. They emit across many wavelengths. Radio waves, from pulsars, beams sweeping across the galaxy. This is how most pulsars are discovered. X-rays, from the hot surface. Young neutron stars, still cooling, glow in X-rays. The Chandra X-ray Observatory can detect them, map their surface temperatures, look for hot spots. Gamma rays, from magnetars. When a starquake fractures a crust, when a magnetic field reconfigures explosively, a flare of gamma rays bursts outward. The Fermi Gamma Ray Space Telescope watches for these events, even optical light. For the fastest spinning pulsars, millisecond pulsars, the surface might be hot enough to emit faint visible light. The Hubble Space Telescope has imaged a few. Each wavelength reveals something different. Radio tells us about the magnetosphere, the beams, the rotation. X-rays tell us about the surface, the temperature, the cooling rate. Gamma rays tell us about the magnetic field, the energy stored, the violence. Optical light, rare and faint, tells us about the very surface, the materials, the atmosphere if one exists. To understand a neutron star fully, we need to observe it in all these wavelengths, build a complete picture, multi-wavelength astronomy. It's like viewing a landscape in different lights. Sunrise, noon, sunset, infrared. Each reveals different features, different truths. Your perception is shifting wavelengths too, from the bright visible light of consciousness to the dim infrared of drowsiness, to the radio waves of deep sleep. Each wavelength a different state, a different truth. Let the wavelength shift. Let the spectrum slide toward the long, the low, the slow, into sleep. Sometimes a neutron star wobbles, not in its rotation. The rotation is steady, but the axis, the direction of the spin, might press us like a spinning top. As it slows, it starts to wobble. The axis traces out a cone. This is precession. For a neutron star, precession can occur if the star isn't perfectly symmetric, if it has a slight bulge, or if the magnetic field exerts a torque. The precession is slow. The axis might complete one wobble every few months, or years, or decades. As the axis wobbles, the beam geometry changes. The angle between the magnetic axis and the spin axis varies. The beams sweep across Earth differently. We see this as a variation in the pulse profile. Sometimes the pulse is stronger, sometimes weaker. Sometimes the pulse shape changes. These variations are predictable. regular. We can model them, understand them. Some pulsars show clear precession, others don't. It depends on the internal structure, the magnetic field strength, the exact shape of the star. Precession is a form of wobble, a slow oscillation, a wandering of the axis. Your axis is wobbling too, the axis of consciousness, the focus of attention. It's drifting, precessing, the direction of thought wandering, unfocused. Let the wobble continue. Let the axis drift. Let precession deepen into randomness. No fixed direction. No steady axis. Just drift over millions of years. Something interesting happens to a pulsar's magnetic field. Remember that the magnetic axis and the spin axis are often misaligned. That misalignment is what creates the sweeping beams, the lighthouse effect. But the misalignment doesn't last forever. The magnetic field isn't perfectly rigid. It can twist, reconnect, evolve, and the star's rotation, the spinning, exerts torques on the field. The field lines want to align with the spin axis to minimize energy. Gradually, over eons, the magnetic field realigns. The angle between the magnetic axis and the spin axis decreases. The wobble of the beam becomes smaller, the sweep less dramatic. Eventually, after millions or tens of millions of years, the magnetic axis might align perfectly with the spin axis. At that point, the beams stop sweeping. They become symmetric, unchanging. The pulsar becomes invisible, even though it's still spinning, even though it's still emitting. We can't see it anymore. The beam no longer sweeps past Earth. The pulsar is aligned, and in aligning, it has disappeared from our view. This is one way pulsars die. Not by stopping, but by becoming unobservable. Alignment, symmetry, it leads to invisibility. Your thoughts are aligning now too, settling, becoming more uniform, less variable, the mental wobble decreasing, the sweep of awareness narrowing, steadying. Soon, alignment will be complete. All variation will cease, and consciousness will become symmetric. Still, sleep, there's a boundary in parameter space, a line that separates active pulsars from dead ones. It's called the death line. As a pulsar spins down, as it loses energy and slows, the conditions in the magnetosphere change. The electric fields weaken. The acceleration gaps shrink. Particles accelerate less efficiently. And at some point, the pulsar can no longer create electron-positron pairs. Pair production ceases. Without pair production, there's no plasma in the magnetosphere, no current, no coherent radio emission. The pulsar goes quiet. It's still there, still spinning, still magnetic, but it's radio silent, dead. The exact location of the death line depends on the magnetic field strength and the rotation period. Strong field pulsars can remain active longer. Weak field pulsars die sooner. Most pulsars cross the death line after about 10 million years. They spin down below the critical rate. Pair production stops. The radio emission ceases. They become ghosts. Invisible, undetectable. The galaxy is full of these dead pulsars, former lighthouses, now dark. They outnumber the active pulsars by perhaps 10 to 1 or more. Silent, spinning, unknown. You are approaching a death line too, the line between wake and sleep, the boundary where wakefulness ceases. Soon you'll cross it. Consciousness will stop. The emission of thoughts will end. You'll become quiet, silent, at rest. Let the line approach. Let the boundary near. Let yourself cross over into the quiet, into the dark, into sleep. How many neutron stars are there in the Milky Way? We detected a few thousand pulsars, but that's just a tiny fraction. Most neutron stars are invisible, radio quiet, or their beams don't sweep past Earth, or they're too faint, too distant, based on supernova rates, based on stellar evolution models. Astronomers estimate there are about 100 million neutron stars in our galaxy. 100 million. Most are old, cold, slow spinning. They emit nothing we can detect. They drift through the galaxy, invisible, silent, forgotten. Some are in binary systems, orbiting companion stars. These we might detect through other means. X-ray emission from accretion, timing variations from the orbit, but most are isolated, alone, moving through the galactic disk or halo, unseen. The Milky Way is full of these dark remnants, stellar corpses, the end product of massive stars that lived and died billions of years ago. They're everywhere, perhaps one within a few light years of Earth, perhaps several within 10 light years. We don't know. We can't see them. The galaxy is more crowded than it appears, full of invisible mass, dark objects, neutron stars, black holes, brown dwarfs. Most of the universe is dark, hidden, unobserved. You are drifting into that darkness now, joining the silent majority, the unobserved, the quiet. Let yourself become one of 100 million, invisible, at rest, of those 100 million neutron stars. Most are old. They were born billions of years ago, when the galaxy was young, when star formation was more vigorous. They've been spinning down ever since, slowing, cooling, fading. Their rotation periods are now measured in seconds, or tens of seconds. Far too slow for pair production, far below the death line. Their surface temperatures have dropped to below 10,000 Kelvin, still hot by human standards, but cool for a neutron star, emitting primarily in infrared. Faintly, they're nearly invisible. Occasionally, very occasionally, one is spotted. A survey happens to point at just the right location. A faint infrared source is detected. Follow-up observations confirm it's a neutron star. But these discoveries are rare, serendipitous. Lucky. Most of the silent population remains undetected. Unknown, they make up the vast majority of neutron stars, perhaps 99%. They're there, orbiting the galaxy, slowly cooling, slowly drifting, but we'll never see most of them. They're too faint, too cold, too silent. They exist beyond observation, real but unreachable. The universe doesn't require our observation to exist. Most of it unfolds unseen, unknown, and that's okay. Not everything needs to be known, cataloged, studied. Some things can simply be quietly, invisibly, like sleep, happening unseen, unobserved, real but interior. Let yourself join the silent population, undetected, at rest. For a neutron star in isolation, no companion star to interact with, no source of new energy. The aging process is simple. It spins down. The magnetic field gradually weakens. The surface cools. Over the first million years, it cools from millions of Kelvin to perhaps 100,000 Kelvin. Over the next 10 million years, it cools to 10,000 Kelvin. Over the next billion years, it might cool to 1,000 Kelvin or less. At these temperatures, it emits in the far infrared or radio waves, weak thermal radiation. Ancient neutron stars, born when the universe was young, might have cooled to just a few hundred Kelvin, barely warmer than the cosmic microwave background. They're nearly impossible to detect. Dark, cold, silent, they drift through the galaxy, occasionally passing through a giant molecular cloud, disturbing the gas slightly, creating a faint wake, or passing close to a star, perturbing its orbit slightly, a gravitational ripple. But mostly they move unseen, ghosts of dead stars, wandering eternally. There's something peaceful about that, existing without interaction, moving through space without disturbance. No obligation to shine, no need to pulse, just drifting. You are drifting too, isolated, aging, cooling into sleep. No need to interact, no need to shine. Just drift. Let the ancient process continue. Let the cooling deepen. Let the drift carry you into the dark, into the cold, into sleep. Not all pulsars slow down into silence. A special few are recycled. If a neutron star is in a binary system, orbiting a companion star, it might accrete matter. As the companion star ages and expands, it sheds its outer layers. Some of this material falls onto the neutron star. The material carries angular momentum. As it spirals inward, it spins up the neutron star. Faster, faster, over millions of years of accretion. The neutron star can be spun up to incredible speeds, hundreds of rotations per second. These are called millisecond pulsars. Their periods are measured in milliseconds, a few thousandths of a second per rotation. The first millisecond pulsar discovered was PSR B 1937 plus 21. found in 1982. It rotates 642 times per second. 642. That's extraordinary. The surface of the equator is moving at about 10% of the speed of light. The star is flattened by centrifugal force, distorted from a sphere into an oblate shape, but it holds together. Gravity is strong enough. Millisecond pulsars are incredibly stable. Their rotation periods vary by less than 1 part in 10 to 15th. They're the most precise natural clocks in the universe. Astronomers use them for all sorts of things: testing general relativity, detecting gravitational waves, navigating spacecraft. These recycled pulsars, given new life by accretion, spun up from the edge of death back to vigorous activity. They'll spin for billions of years more, slowly, very slowly, spinning down, but so slowly that it hardly matters. Recycling, renewal, a second life. Your sleep is a recycling too, a renewal. Your body, tired from the day, will be refreshed, spun up, ready for tomorrow. Let the recycling begin. Let the renewal start. Let sleep restore you. Rest now. Spin down into sleep and wake renewed. We just discussed millisecond pulsars, those rapidly spinning neutron stars. But where do they come from? They're recycled. Imagine an old neutron star. It's been spinning for hundreds of millions of years. Slowly, quietly, it crossed the death line long ago. It's radio silent, nearly invisible, but it's in a binary system. It has a companion star. The companion ages. Eventually it expands, becomes a red giant. Its outer layers swell outward, and the neutron star, patient, waiting, begins to accrete this material. The gas spirals inward, forms an accretion disk. Gradually, particle by particle, it falls onto the neutron star. Each particle carries angular momentum. The neutron star absorbs this momentum. It spins faster, over millions or billions of years. The neutron star is spun up from a slow rotator to a fast one, from perhaps 1 rotation per second to 10 to 100 to several hundred. The dead pulsar is resurrected, recycled, given new life. Its magnetic field, though weakened by age, is still strong enough. The rapid rotation creates the conditions for pair production again. The magnetosphere activates. Radio emission returns. A millisecond pulsar is born, or rather reborn. This recycling process is common. Perhaps half of all millisecond pulsars were created this way. Old neutron stars given a second chance, a new beginning. Rest is recycling too. Sleep recycles your energy, your focus, your metabolic resources. You awake renewed, recycled, ready. Let the recycling begin. Let sleep restore you. The recycling scenario is a beautiful story, a cosmic narrative of decay and renewal. A neutron star is born, young, hot, spinning rapidly, magnetic field at maximum strength, perhaps 10 to the 12th or 10 to the 13th Gauss. It emits, it pulses, it shines in radio and X-rays, but over millions of years, it spins down. The magnetic dipole radiation carries away rotational energy. The period lengthens. As it slows, the magnetic field decays too. Ohmic dissipation. Currents in the crust slowly die away. The field weakens. After 10 million years, the pulsar crosses a death line. Radio emission ceases. After 100 million years, the field has weakened to 10 to the 10th Gauss. The star is cold, slow, silent. It drifts, a dead pulsar, invisible, but if it has a companion. Billions of years later, the companion evolves, expands. Mass transfer begins. Accretion spins a neutron star up. Faster, faster. The weakened magnetic field, now only 10 to the 8th or 10 to the 9th Gauss, is sufficient at high rotation rates. Even a weak field can create pair production. The magnetosphere reactivates. The pulsar shines again, bright, millisecond pulses, from death to rebirth, from silence to song. The cycle of stellar evolution, complex, multi-stage, beautiful in its intricacy. Nothing is truly dead in the universe, just dormant, waiting for the right conditions to awaken. Your body cycles too. Wake and sleep, activity and rest. Over and over. Let the cycle continue. Let sleep come. You'll wake again. Renewed. The magnetic field of a neutron star is not constant. It evolves, decays. Young neutron stars, magnetars especially, can have fields up to 10 to the 15th Gauss, a quadrillion times Earth's field. These ultra-strong fields are unsustainable. The currents that generate them flow in the crust and core. And these currents encounter resistance, ohmic dissipation, electrical resistance. The currents generate heat and slowly die away. Over millions of years, the field weakens from 10 to the 15 Gauss down to 10 to the 12. Still strong, but weaker over tens of millions of years, down to 10 to the 10 Gauss. Old neutron stars, billions of years old, might have fields as weak as 10 to the 8th Gauss, still 100 million times Earth's field, but weak by neutron star standards. This decay is inevitable, irreversible. The field drains away like a battery slowly discharging. But here's the interesting thing. Recycled pulsars, millisecond pulsars spun up by accretion, have weak fields. They're old. Their fields have had billions of years to decay. And yet, they pulse. They emit, because rotation matters more than field strength. A weak field rotating rapidly can do the same job as a strong field rotating slowly. Everything decays. Everything weakens. But adaptation is possible. New strategies. New configurations. Your energy is decaying now. weakening. But that's okay. You don't need high energy to rest. Weakness is appropriate for sleep. Let the field decay. Let energy drain. Let strength fade into rest, into sleep. Millisecond pulsars, with their extraordinary stability, can be used for something remarkable, detecting gravitational waves. Not the high-frequency gravitational waves from merging neutron stars or black holes. Those are detected by LIGO and Virgo, but low-frequency gravitational waves, nanohertz frequencies, waves with periods of months or years. These come from supermassive black hole binaries, two black holes, each millions or billions of solar masses orbiting each other at the centers of distant galaxies. As they orbit, they generate gravitational waves, space ripples, but very slowly. The waves stretch and squeeze space with periods of years. How do we detect such slow oscillations? By watching pulsars. Astronomers observe dozens of millisecond pulsars scattered across the sky. They record the exact arrival time of each pulse. For years, for decades, these pulsars are incredibly stable. The pulse arrival times are predictable. But if a gravitational wave passes between Earth and a pulsar, it distorts space. It changes the travel time of the pulses, slightly, by nanoseconds. By correlating the timing variations from many pulsars, a network, an array, astronomers can detect the gravitational wave signal. It's called a pulsar timing array, a galaxy-scale detector, using pulsars as the measurement devices. And in 2023, the arrays detected a signal, a background hum of gravitational waves, from countless supermassive black hole binaries throughout the universe. The universe is ringing, vibrating, at frequencies we can barely measure. But pulsars, those stable lighthouses, reveal the vibrations. Everything is connected. Everything influences everything else. Across vast distances, across time, let yourself feel connected, part of the universe, influenced by its rhythms. Let the slow oscillations of sleep approach. Let the gravitational wave of drowsiness wash over you. Millisecond pulsars are so stable, so predictable, that they can be used for navigation. Not on Earth. GPS does that job well. But in deep space, far from Earth, where GPS satellites don't reach, a spacecraft traveling to the outer solar system or beyond needs to know where it is, its position, its velocity. Radio signals to and from Earth work, but they're slow. At the distance of Jupiter, radio signals take over half an hour to travel one way. Conversations are difficult, but pulsars pulse. Constantly, everywhere. A spacecraft equipped with an X-ray detector can observe pulsars, measure the arrival times of pulses, compare them to predictions. From the timing differences, the spacecraft can calculate its position to within a few kilometers. Even at distances of tens of thousands of astronomical units, NASA's nicer, The Neutron Star Interior Composition Explorer has demonstrated this. NICER is an X-ray telescope on the International Space Station. It observes millisecond pulsars, tests pulsar navigation. It works. The precision is extraordinary. In the future, deep space missions might navigate using pulsars, natural beacons, galactic lighthouses, providing position information anywhere in the solar system or beyond. We navigate using the stars. Ancient mariners did. Modern spacecraft do. Different stars, different methods, but the same principle. The universe guides us if we pay attention. If we listen, you're navigating now towards sleep. The pulsars of your body, heartbeat, breath, guide you. Let them guide you. Let the rhythm lead. Let navigation become automatic. Toward rest, toward sleep. Pulsars are stable. Their rotation is steady, predictable, but occasionally, very occasionally, something strange happens. A pulsar suddenly spins faster, just a tiny bit, a few microseconds shorter period. Then, over days or weeks, it slowly relaxes back. Not quite to the original period, but close. This is called a glitch. The pulsar glitched. Its rotation rate jumped. Why? The leading theory involves a crust and the superfluid interior. Remember that the core is a superfluid. It flows without friction. When the crust slows down due to magnetic braking, the superfluid core doesn't slow at the same rate. A differential rotation builds up. The core spins faster than the crust. This is mediated by vortices, tiny whirlpools in the superfluid. These vortices can pin to the crust, attach themselves. This transfers some angular momentum. But as the differential rotation increases, the stress on the pinned vortices increases. Eventually, the crust fractures. A starquake, the structure adjusts. And suddenly, many vortices unpin simultaneously. Angular momentum transfers from the superfluid core to the crust. The crust spins up, a glitch. It's a sudden release, like an earthquake. Built up stress released in a moment. The pulsar rings, oscillates, then settles, until the next glitch. Years later perhaps, you experience glitches too, sudden adjustments. Micro-wakes during the night, shifts in sleep stage. They're normal, the system adjusting, releasing stress, settling. Let the glitches happen. Let the adjustments occur. Let your sleep cycle naturally. Let's explore this glitch mechanism more carefully. The pinning model. The superfluid in the neutron star core contains vortices. These are quantum vortices. Each one has the same circulation, the same angular momentum. The vortices are arranged in a regular array, like a lattice, parallel lines extending through the superfluid. When the star rotates, the vortices mimic solid body rotation. They move through the superfluid, migrating outward slowly. But the crust, the solid outer layer, impedes them. Vortices can pin to impurities in the crust, to nuclei, to irregularities in the structure. When pinned, the vortices can't move. They're stuck. As the crust slows down due to magnetic braking, the vortices remain pinned. The superfluid, which contains most of the angular momentum, doesn't slow at the same rate. A lag develops. The superfluid spins faster than the crust. The pinned vortices act like a clutch, transferring some angular momentum, but not all. Eventually, the stress becomes too great. The crust fractures in a starquake. The vortices unpin en masse. Suddenly, a large amount of angular momentum transfers from the core to the crust. The crust spins up, a glitch. After the glitch, the process begins again. Vortices repin. Differential rotation builds up. Another glitch years later. It's a cycle. Stress and release. Build up and discharge. Like your sleep. Tension and relaxation. Wakefulness and rest. Let the pin tension release. Let the vortices unpin. Let angular momentum distribute evenly into stillness, into sleep, between glitches during the slow buildup of differential rotation. The vortices are not completely static. They creep. Even though pinned, they can slowly migrate. Quantum tunneling allows them to hop from one pinning site to another, moving outward gradually. This is called vortex creep. As they creep, they carry angular momentum outward, from the superfluid core to the crust. This partially offsets the magnetic braking. It slows the buildup of differential rotation, but the creep is slow, not fast enough to prevent glitches entirely. Over years, creep transfers some angular momentum. The gradient rebuilds. Stress increases. Then glitch. Sudden transfer. Release. Then creep begins again. The interplay between creep and glitch determines the glitch frequency. How often glitches occur. How large they are. Some pulsars glitch frequently, every few years. Others rarely, once per century. It depends on the internal structure, the pinning strength, the superfluid properties. Creep is slow change, gradual, imperceptible moment to moment, but significant over time. Your drift into sleep is like creep. Gradual, slow migration from wakefulness to drowsiness, from drowsiness to sleep. Imperceptible moment to moment, but significant, real. Let the creep continue. Let the slow migration proceed. Let yourself drift outward, into rest. The Vela pulsar is one of the best studied glitching pulsars. It's relatively nearby, about 1,000 light years away, bright in radio and X-rays, and it glitches regularly. Every 3 to 4 years on average. Each glitch is small. The period decreases by about 10 microseconds, out of a period of 89 milliseconds. A fractional change of about 1 part in 100,000. Tiny, but measurable, After the glitch, the pulsar slowly relaxes. Over weeks, the period gradually increases again. Not quite back to the pre-glitch value, but close. Astronomers have observed dozens of Vela glitches. They've studied them in detail, modeled them, used them to understand the interior structure. The glitches are thought to be starquakes, sudden fractures in the crust, releasing pinned superfluid vortices. The regularity suggests a regular stress accumulation. As the pulsar spins down, strain builds in crust. Eventually, the crust can't support it. Fracture. The Vela pulsar is young, only about 10,000 years old. Its crust is still adjusting, settling, releasing stress. Older pulsars glitch less frequently. Their crusts have settled. The structure is more stable. But Vela, young and active, glitches regularly. A cosmic clock of a different kind, marking time not with steady pulses, but with occasional jumps. Your sleep will have jumps too. Transitions between sleep stages. REM to deep sleep to light. Micro-wakes. They're normal, part of the cycle. Let them happen. You're settling, like a young pulsar, adjusting to rest. Finally, a mystery, an oddity, something rare and strange. One pulsar, PSR J0538 plus 2817, has been observed to anti-glitch. Instead of spinning up suddenly, it spun down. In 2018, astronomers noticed that its period had increased. The pulsar was rotating more slowly, by a tiny fraction, but measurably. An anti-glitch. This shouldn't happen according to the standard model. Glitches occur when angular momentum transfers from the fast-spinning superfluid core to the slower crust. The crust speeds up. An anti-glitch will require the reverse. Angular momentum transferring from the crust to the core. The crust slowing down. How is this possible? One theory involves reverse vortex motion. Perhaps in certain conditions, the superfluid vortices can move inward, carrying angular momentum from the crust to the core. Or perhaps the magnetic field configuration changed. A sudden reorganization, transferring angular momentum differently. We don't know. Anti-glitches are rare. Only a few have been observed. The mechanism is unclear. It's a reminder that neutron stars still hold mysteries, things we don't understand, behaviors that surprise us. The universe is not fully known, not fully understood. There are still surprises, still mysteries, and that's beautiful. That's wonderful. There's more to learn, more to discover. Your sleep holds mysteries too, dreams you won't remember, neural processes you're unaware of, restoration you can't perceive. Let the mystery unfold. Let the unknown happen. You don't need to understand. Just rest. Just sleep. Let this final fact carry you into darkness, into mystery, into the beautiful unknown of sleep. Good night. Rest well. Let the neutron stars spin in the darkness. and let yourself finally sleep. Young neutron stars don't just spin. They breathe. They exhale particles. Electrons, positrons, ions, streaming outward from the magnetic poles at nearly the speed of light. This is called a pulsar wind. The particles are accelerated by the intense electric fields in the magnetosphere. They spiral along magnetic field lines. They accelerate faster, faster, until they're moving at 90%, 95%, 99% of light speed. Relativistic, almost as fast as anything can go. These winds carry enormous energy, power, stolen from the pulsar's rotation. The pulsar spins down, and the wind carries that rotational energy outward into space. When the wind slams into the surrounding supernova remnant, into the expanding shell of gas from the original explosion, it creates a shock, a bubble, a cavity. This bubble is called a plerion, or a pulsar wind nebula. The Crab Nebula is the most famous example. At its heart, a young pulsar spinning 30 times per second, breathing out a wind of particles at nearly light speed. The wind inflates the nebula, fills it with energetic particles, makes it glow. From Earth, through a telescope, the Crab Nebula looks like a delicate, beautiful cloud, filaments of gas, glowing regions, but it's powered by violence, by a wind blowing at relativistic speeds, by particles accelerated to unimaginable energies. Beauty and violence, intertwined, inseparable. Your breath is a wind too, slower, much slower, but steady, regular. Let it slow further. Let the wind gentle. Let exhalation lengthen. Breathe out. Release. Let the wind carry tension away. The particles in a pulsar wind, electrons and positrons moving at nearly light speed, don't travel in straight lines. They spiral around magnetic field lines, caught in the field, trapped. And when charged particles spiral, when they accelerate in curved paths, they radiate. This is called synchrotron radiation. The faster the particle moves, the more energetic the radiation. Relativistic particles, moving at 99% of light speed, emit high-energy photons, X-rays, gamma rays, but they also emit lower energies, radio waves, visible light. The radiation is polarized. The electric field oscillates in a specific direction. This polarization reveals the magnetic field structure, the geometry of the wind. Synchrotron radiation is what makes pulsar wind nebulae glow. The Crab Nebula glows in synchrotron light, blue-white, brilliant, powered by the Crab pulsar's wind. The Vela Nebula, another plerion, glows too, fainter, older, but still visible. These nebulae are laboratories. We can study particle acceleration, magnetic field structure, energy transport, all by observing the glow. The light is secondary, a byproduct. The real story is the particles, the wind, the energy, but we see only the light, the visible evidence, the glow. Your thoughts glow too. Consciousness is the glow of neural activity, the visible evidence of underlying processes. As you drift towards sleep, the glow fades, the activity quiets, the synchrotron of thought slows. Let the glow dim, let the radiation decrease, let visibility fade. Into darkness, into sleep. The Crab Nebula pulsar is young, very young by astronomical standards. It was born on July 4th, 1054 AD. We know this because people saw it. Chinese astronomers recorded a guest star appearing in the constellation Taurus, bright enough to see in daylight, visible for 23 days. It was a supernova, the explosion that created the Crab Nebula, and the pulsar at its heart. That was 970 years ago. In human terms, ancient. In cosmic terms, yesterday. The pulsar is still young, still energetic, still spinning rapidly. 30 rotations per second, fast by normal pulsar standards, though not as fast as millisecond pulsars. But what makes it special is the energy output. The pulsar powers the entire nebula. The glow, the motion, the expansion. The nebula is 6 light years across now, still growing, expanding at about 1,500 kilometers per second. And at the center, the pulsar, barely visible, a faint star, but the engine driving everything. 1,000 years from now, the pulsar will still be there, spinning, slowing, powering the nebula. 10,000 years from now, it will be slower, fainter, but still active. Youth is relative. 1,000-year-old pulsar is young. A billion-year-old pulsar is old. But both exist simultaneously in the galaxy, young and old, fast and slow, bright and dim, all stages of life, all at once. You are young in some ways, old in others. It doesn't matter. All stages are valid. Rest now, whatever your age. Whatever your stage, let the crab pulsar spin in your imagination, bright, energetic, while you slow dim, rest. If the crab pulsar is young at 970 years, there are even younger ones. PSR J 1357-6429. A pulsar in the southern sky. Age, approximately 1,700 years, perhaps less. This makes it one of the youngest known pulsars. Born around the year 300 AD, during the Roman Empire, the Han Dynasty in China. No one recorded the supernova. Either it wasn't visible from Earth, hidden behind dust perhaps, or it occurred during a time when no one was watching that part of the sky. But the pulsar is there, young, hot, bright. Its luminosity is 10 to the 35 ergs per second. That's 100 billion times more powerful than the sun. Most of this energy is in X-rays. The surface is still hot, still glowing from the heat of birth. The pulsar is spinning quickly, and slowing rapidly, losing energy at a tremendous rate. In a few thousand years, it will have cooled considerably, slowed noticeably, become more ordinary. But now, it's in the bloom of youth, energetic, radiant, powerful. Youth doesn't last, for pulsars or for people or for anything, but it's beautiful while it's here. You were young once, energetic, radiant. Now, perhaps you're older, cooler, slower. That's okay. Every stage has its beauty. Youth is bright. Age is peaceful. Rest in whatever stage you're in. Let the young pulsar spin far away, while you here rest. When a massive star explodes, the supernova is rarely symmetric. Material doesn't eject evenly in all directions. One side might be heavier, more massive, moving faster. And by conservation of momentum, if more material goes out one side, the remnant, the neutron star, must recoil the other way, like a gun recoiling when it fires. The bullet goes forward, the gun goes backward. The neutron star gets a kick, sometimes a gentle kick, a few tens of kilometers per second, enough to give it a modest motion through the galaxy. But sometimes the kick is enormous. Some neutron stars are moving at over 1,000 kilometers per second. 1,000. That's 3 million kilometers per hour. Fast enough to cross the diameter of Earth in about 4 seconds. At these speeds, the neutron star becomes a runaway. It leaves the region where it was born, moves through the galaxy, might even escape the galaxy entirely if the kick was strong enough. Some of these runaways form interesting systems. If they happen to pass close to another star, they might capture it, or be captured, form a binary system. Black Widow pulsars are one example. A rapidly spinning pulsar in orbit with a low-mass star. The pulsar's radiation, its wind, slowly evaporates a companion. The companion is doomed, being consumed, hence the name, Black Widow. These systems are rare, unusual, created by chance encounters between runaway neutron stars and unsuspecting stars. Everything moves. Nothing is truly at rest. Stars drift. Galaxies merge. Motion is universal. Even you, lying still, you're moving. Earth rotates, orbits the sun orbits the galaxy moves through space. But relative to your bed, you're still, and that's what matters. Let absolute motion continue. Let the galaxy move. Let runaway neutron stars zip through the void. Here, now you are still, at rest, unmoving. Let stillness deepen. Let motion fade from perception. Rest. Some neutron stars are close enough and moving fast enough that we can see them move across the sky. Not with the naked eye. They're far too faint. But with telescopes. Over years, decades, the position of the neutron star shifts. Slightly, measurably. This is called proper motion. By measuring the proper motion, Astronomers can trace the neutron star's path backward, like rewinding a film, running time in reverse. Where was the neutron star 10,000 years ago? 100,000 years ago? Trace it back far enough, and you reach the point of origin, the place where it was born. Sometimes there's a supernova remnant there, an expanding shell of gas. Confirmation. The neutron star was born here, kicked outward, traveled all this way. By measuring the distance and the time, we can estimate the kick velocity, how fast it was moving when it was born. This helps us understand supernova asymmetries, the physics of the explosion, the mechanisms that create kicks. Everything has a history, a trajectory, a path from origin to present. You have a path too, from birth to now, through space and time, through experiences and memories. But the past is past. The trajectory led here, to this moment, this bed, this quiet room. Let the past recede. Let the trajectory settle. You've arrived. You're here. No need to trace backward. No need to rewind. Just be here, now, at rest. In 2009, the Chandra X-ray Observatory began observing a particular neutron star, a young one, moving rapidly, trailing a wake of X-ray emission as it plowed through the interstellar medium. Chandra observed it repeatedly, year after year, precisely measuring its position each time. By 2024, 15 years of data, 15 precise measurements. And from these measurements, astronomers could calculate the neutron star's velocity, its direction, its origin. They traced it backward, rewound its motion, and they found the supernova remnant, the expanding debris from the original explosion. The neutron star had been kicked violently in the opposite direction from the bulk of the ejected material. Conservation of momentum. The debris went one way. The neutron star went the other. The kick velocity was over 1,000 kilometers per second. Enormous. The neutron star is now dozens of light years from where it was born. Still moving, still traveling. It will continue for millions of years. Eventually, it might leave the galactic disk entirely, heading into the halo, or beyond. 15 years of patient observation, careful measurement, and a complete story emerges. Science requires patience, attention, long-term commitment, but the rewards, understanding, insight, truth. You've been patient tonight too, listening, drifting, slowly settling towards sleep. The reward is coming. Rest, renewal, dreams. Let the last measurements complete. Let the trajectory finalize. Let arrival be imminent. Soon, very soon, on February 23rd, 1987, a star exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light years away. The supernova was visible to the naked eye, the brightest supernova seen from Earth since 1604. Astronomers around the world observed it intensely. Supernova 1987A. The explosion was asymmetric, unusual. It produced strange rings of glowing gas, a triple ring structure never seen before. And at the center, where the star had been, there should be a neutron star. Theory predicted it. The core should have collapsed. A neutron star should remain. But no one could find it. Radio observations, nothing. X-ray observations, nothing. Optical, nothing. The neutron star was hidden, obscured, either by dust, or emitting too faintly, or somehow not there at all. For 37 years, astronomers searched, looked, hoped. Instruments improved. Telescopes launched. Chandra, Hubble, Alma. Still, no clear detection. Had the core collapsed directly to a black hole? Was the neutron star too faint? Too obscured? The mystery endured for decades. But patience eventually is rewarded. In 2024, the James Webb Space Telescope observed SN 1987A with unprecedented sensitivity in infrared light, and it found something, a compact source. At the center, a neutron star. Finally, after 37 years, the search was over. The mystery solved. Patience and persistence. Over decades. Rewarded. Your patience tonight is nearly rewarded too. Sleep is close. So close. Let the search end. Let the mystery resolve. Let rest finally arrive. The James Webb Space Telescope, JWST, is the most powerful infrared observatory ever built. Launched in December 2021. Deployed to a point 1.5 million kilometers from Earth. Beyond the moon, in deep space, it can see through dust, detect faint infrared sources, resolve details invisible to other telescopes. In 2024, it turned its attention to supernova 1987A, and it saw something remarkable. Not just a neutron star, though it detected that too, but a structure, a cavity, a hole in the surrounding material. The neutron star had been kicked violently during the supernova explosion. It had plowed through the material around it, pushing it aside, creating a tunnel, a kick hole. The hole was offset from the center of the remnant, evidence of the neutron star's motion, its trajectory. JWST imaged this hole directly for the first time. Confirmation, proof. The neutron star had received a supernova kick. It was offset, moving. 37 years of mystery, solved by a single telescope, a few observations. Sometimes answers come suddenly, after long waiting. Sometimes clarity arrives all at once. Your clarity is arriving too. The clarity of sleep, the resolution of wakefulness into rest. Let JWST's patient observation inspire you. Wait, watch, and then suddenly arrival. The kick hole is beautiful in a strange cosmic way. cavity, a tunnel, a void carved through glowing gas. JWST's image shows it clearly, a dark region, offset from center, where the neutron star passed through. The gas around the hole glows in infrared, heated by the neutron star's radiation, by the shocks from its passage. The hole itself is darker, less emission, the material pushed aside. It's direct evidence, visual proof of the violence of neutron star birth. The kick wasn't gentle. It was explosive, powerful, sufficient to blast a tunnel through supernova debris. And now, 37 years later, the tunnel remains, visible, a scar in space. Everything that happens leaves a mark, an impression, a trace. The supernova left a remnant. The neutron star left a hole. You, lying here, leave an impression in the mattress, a warmth in the sheets, evidence of presence, of existence. But soon you'll drift into sleep. The impressions will soften. The marks will fade into the gentle darkness, into the quiet void. Let the kickhole image fade from your mind. Let the neutron star drift away. Let the 37-year search conclude. And let yourself finally, completely fall into the beautiful darkness of sleep. Rest well, dream gently, and let the neutron stars, those distant, violent, beautiful objects, continue their eternal dance. While you sleep, not all neutron stars are alone. Many have companions. Another star, orbiting, bound by gravity, dancing through space together. Binary systems, two objects, locked in eternal orbit, circling a common center of mass. When a neutron star has a normal star as a companion, something beautiful and violent happens. The neutron star's gravity is immense. It pulls, tugs, distorts the companion star. If the companion is close enough, material from its surface begins to fall toward the neutron star. Gas, plasma, streaming across the space between them. This material doesn't fall directly onto the neutron star. It has angular momentum. It spirals inward, forms a disk, an accretion disk. The disk glows. Hot gas compressed, heated by friction. Temperatures reach millions of degrees. The disk radiates. X-rays stream outward. The binary becomes an X-ray source, visible from across the galaxy, a beacon announcing the presence of a feeding neutron star. Sometimes the accretion is steady, a constant stream. The X-rays glow continuously. Sometimes it's variable, unstable. The disk flickers, brightens and dims. But always, the neutron star feeds, growing, spinning up, gaining mass and angular momentum from its companion. A cosmic partnership, one star giving, the other taking, an exchange that will continue for millions of years. Partnerships exist everywhere. Give and take, balance, exchange. Your body is in partnership with itself. heart and lungs, brain and muscles, each supporting the other. As you sleep, the partnership continues, automatically, without thought, without effort. Let the partnership of your systems carry you into rest, into renewal, like binary stars, dancing, eternal, together. The process of mass transfer in a binary system follows specific rules. Every star has a region around it, a three-dimensional surface called the Roche lobe. Inside this boundary, material is gravitationally bound to star. Outside it, material can transfer to the companion. When a star ages, it expands. Red giant phase. Swelling. Eventually, its surface reaches the Roche lobe. Material spills over, like water overflowing a container. This is called Roche lobe overflow. The material flows toward the neutron star, spirals inward, joins the accretion disk. As the neutron star accretes, it gains angular momentum. It spins faster, recycled, reborn as a millisecond pulsar eventually. But the companion, losing mass, shrinks, becomes lighter, smaller. The binary evolves, changes. The neutron star grows stronger, the companion weaker. These systems are called low-mass X-ray binaries. The companion is a low-mass star, less than the Sun, sometimes much less. The X-rays come from the accretion disk, from the hot material spiraling onto the neutron star, bright, visible across the galaxy, announcing the presence of mass transfer. It's a slow erosion, the companion being consumed, fed to the neutron star, over millions of years. Sacrifice, one star giving itself slowly to another. There's something peaceful about slow processes. Erosion, transfer, change over millions of years. No rush, no urgency, just gradual transformation. Let yourself transform gradually too, from wakefulness to sleep, slowly, peacefully, no rush, no urgency. Just drift in a low-mass X-ray binary. The neutron star accretes hydrogen, the most common element in the universe, abundant in normal stars. The hydrogen falls onto the neutron star's surface, layer by layer, atom by atom. But it doesn't just sit there. The neutron star's gravity compresses it, heats it. The temperature rises, the pressure increases. Deep in the accumulated layer, conditions become extreme, hot enough for fusion. But this isn't the steady fusion that powers normal stars. This is unstable. Run away. The hydrogen ignites. All at once, the entire layer fuses in a fraction of a second, an explosion on the surface of the neutron star, a thermonuclear blast, releasing more energy than the sun radiates in hours or days. The explosion creates a burst of X-rays, a sudden brightening, visible from thousands of light years away. The burst lasts seconds, maybe tens of seconds, then fades, the neutron star returns to normal, accreting, building up another layer, and eventually, months or years later, another burst. These are type 1 X-ray bursts, common in accreting neutron stars. Predictable, regular, bursts of energy, sudden, brief, then quiet again. Your consciousness has burst too. Moments of clarity, sudden thoughts, then quiet. As you drift towards sleep, the bursts become less frequent. Longer quiet periods between them. Soon, the bursts will stop entirely. Only quiet will remain. Let the bursts fade. Let the quiet lengthen. Let silence deepen. The physics of these X-ray bursts is fascinating. The accreted fuel, hydrogen and helium, accumulates on the neutron star surface. The gravity is so strong, 200 billion times Earth's, that the layers compress to incredible densities, and the heat from below, from the neutron star's hot interior, warms the base of the layer. Temperature rises, slowly, over hours or days. Eventually, a critical temperature is reached, about 100 million Kelvin. At this temperature, nuclear fusion can begin, but it doesn't start gradually. It explodes. This is a thermonuclear runaway. The fusion reactions release energy. The energy heats the surrounding material. Hotter material fuses faster. More energy, more heating, a feedback loop, exponential, out of control. In milliseconds, the entire layer, accumulated over weeks or months, fuses completely. The energy release is staggering, equivalent to thousands of nuclear bombs, all on the surface of an object the size of a city. But the neutron star barely notices. The explosion happens. The burst shines. X-rays stream outward. And then it's over. The surface cools, returns to normal. The neutron star continues accreting, building another layer, preparing for another burst. In some bright binaries, this happens 100 times per year. Every few days, another burst. Regular, predictable, like clockwork. Explosions can be regular, rhythmic, not chaotic, but ordered. Your heartbeat is an explosion, a pulse, rhythmic, regular, ordered. As you sleep, the rhythm continues, slows slightly, but continues. Let the rhythm carry you. Let the explosions of consciousness fade. Let quiet explosions of dreams begin. Not all X-ray bursts are the same. There are types, categories. Type 1 bursts are the most common. These result from pure helium fusion, or a mix of hydrogen and helium. The burst is brief, seconds to tens of seconds. The rise time is fast. The decay slower. The spectrum is characteristic. Black body radiation from the hot surface, cooling as it fades. Type 1 bursts can be predicted if you know the accretion rate. You can estimate when the next burst will occur. Type 2 bursts are different, rarer, less understood. These include hydrogen burning, more complex fusion chains, longer timescales. The bursts can last minutes. They're harder X-rays. Some neutron stars show only type 1. Others show type 2. Some show both. The type depends on the accretion rate, the composition of the accreted material, the magnetic field strength. Each neutron star is unique. Different history, different companion, different behavior. Categories help us understand, but reality is more nuanced, more complex. Sleep has types too. REM sleep, deep sleep, light sleep. Each serves a purpose. Each has characteristics. But you don't need to control which type. Your brain knows. It cycles through them automatically. Let the cycle happen. Let the types flow. Let sleep, whatever type, come. What happens when a neutron star spins very fast and tries to accrete material? Sometimes the spin wins. The neutron star's magnetic field, rotating with the star, creates a magnetosphere, a region where the field dominates. Accreting material, approaching the neutron star, encounters this magnetosphere. If the neutron star is spinning fast enough, the magnetosphere rotates faster than the material is falling. The rotating magnetic field acts like a propeller. It flings the material away. Centrifugal force. The material is accelerated outward, expelled. Accretion stops. This is called the propeller effect. The neutron star, paradoxically, cannot feed, even though material is available, even though the companion is donating mass. The spin is too fast, the propeller too strong. But over time, the neutron star slows down, magnetic braking, spin down. Eventually, the spin decreases enough. The propeller weakens. And suddenly, accretion can begin. Material falls in. The neutron star feeds. It's a threshold, a transition, from propeller mode to accretion mode. Some neutron stars flip back and forth, spinning up when accreting, becoming a propeller again, then slowing, accreting again, a cycle, repeating, over years or decades. Thresholds exist everywhere, between states, between modes. You're at a threshold now, between wake and sleep, balance, teetering. Soon you'll cross it. The propeller of consciousness will stop. Thoughts will no longer be flung away. Rest will begin. Sleep will accrete. Let the threshold approach. Let the transition happen. Let the propeller stop. Some binary systems are violent, predatory even. A rapidly spinning millisecond pulsar in orbit with a very low-mass star, less than half the sun's mass, sometimes much less. The pulsar, spinning hundreds of times per second, emits intense radiation, X-rays, gamma rays, a powerful wind of particles. This radiation, this wind, bathes a companion star. It heats the side facing the pulsar, thousands of degrees. The surface begins to evaporate. Material boils off, streams away. Some falls back onto the pulsar. Some escapes entirely. The companion is being consumed, slowly, evaporated by the pulsar's radiation. These systems are called Black Widow pulsars or redback pulsars, named after spiders that consume their mates. In black widows, the companion is very light, less than 5% of the sun's mass, almost completely evaporated. In redbacks, the companion is slightly heavier, 10 to 50% of the sun, still being consumed but not yet destroyed. Eventually, millions of years from now, the companion will be gone, completely evaporated. The pulsar will be alone, isolated, still spinning rapidly, but solitary. It's a violent relationship, one partner destroying the other, slowly, inevitably, but also productive. The accretion spun up the pulsar, created the millisecond rotation. Without the companion, the pulsar wouldn't exist in its current form. Relationships transform us, sometimes violently, sometimes destructively, but always they change us. You've been transformed by relationships too. Changed, shaped, but tonight you're alone, solitary, at rest. Let the violence of the day evaporate. Let relationships fade. Let only stillness remain. Alone, peaceful, asleep. In 2024, astronomers discovered an unusual binary system. PSR J1928 plus 1815, a millisecond pulsar, spinning rapidly, but its companion is strange. Not a normal star, not a white dwarf, a helium star, a star made primarily of helium, stripped of its hydrogen envelope, mass between 1 and 1.6 solar masses. Relatively heavy for this type of object. How did this system form? The stars were once closer, much closer, so close that they shared a common envelope. A single cloud of gas surrounding both. Friction in the envelope, drag, caused the orbit to shrink. The star spiraled inward. Eventually, the envelope was ejected, blown away, leaving behind a tight binary. The companion, stripped of its hydrogen layers, became a helium star. This system is rare, only recently discovered, but astronomers estimate there might be 16 to 84 similar systems in the Milky Way, waiting to be found, hidden, undetected. The galaxy is full of rare objects, unusual configurations, waiting for discovery. Most remain unknown, invisible, but they're there. Your dreams tonight will be like undiscovered systems, strange, unique, existing briefly, unremembered. They're there, happening, real, but you won't detect them. Let the rare systems of your mind unfold. Let strange binaries form and dissolve. Let discovery happen without awareness. In sleep, in dreams, undetected. Binary systems are common, but sometimes there are 3 triple systems, 3 objects orbiting, bound by gravity. These are rare, unstable usually. Three-body problem, chaotic orbits. Eventually, one object is ejected, or the system collapses, but some triples are stable. Hierarchical, two objects in a close binary, the third orbiting far away, orbiting the pair. PSR J0337 plus 1715 is one such system, and it's extraordinary. At the center, a millisecond pulsar, spinning 366 times per second. It orbits a white dwarf, a close companion. Orbital period 1.6 days. And farther out, another white dwarf, orbiting both. Orbital period 327 days. Three objects, two white dwarfs and a pulsar, all in one system. This configuration is perfect for testing general relativity, the theory of gravity. The pulsar's timing is so precise, any deviation from prediction, any anomaly, reveals new physics. The gravitational interactions between three massive objects create subtle effects, predicted by general relativity. Measurable, astronomers watch, measure, compare to theory. So far, general relativity passes every test perfectly, but they keep watching, keep measuring, looking for the moment when theory fails. When new physics emerges, three objects dancing, testing the laws of the universe. Your mind, body, and environment form a triple system too, interacting, influencing each other. But tonight, let the interactions quiet, let the dance slow, let the system settle into stillness. Three parts, one rest, together. Some neutron stars don't stay in one mode. They transition. J1023, a remarkable system, a neutron star in a binary. Sometimes it accretes. Material falls from the companion. An accretion disk forms. X-rays shine. The system is an X-ray binary, powered by accretion. But then, mysteriously, the accretion stops. The disk disappears. The X-rays fade. And the neutron star becomes a radio pulsar, spinning, pulsing, beaming radio waves. A complete transformation from one state to another, and then months or years later, it switches back. Accretion resumes. The X-rays return. The radio pulses stop, back and forth, transitioning between modes. Why? We don't fully understand. Something in the system changes. The accretion rate, the magnetic field configuration. But it's invaluable for science. The same neutron star in different states. We can compare, study, understand. In 2024, the IXB satellite, the Imaging X-ray Polarimetry Explorer, observed J1023 in both states, measured the polarization of the radiation, the orientation of the electric field, and found similarities. The emission mechanisms, though different in detail, are related, unified, the same physics, different manifestations. Transitions reveal truth. The moment of change shows what's essential, what remains constant. You're in transition now, from wake to sleep, from activity to rest. In the transition, something essential remains. Your being, your consciousness, transforming but continuous. Let the transition complete. Let the final mode engage. Let sleep finally arrive, rest, transform, and wake renewed. Sometimes what we think we understand turns out to be wrong. PSR J1023 plus 0038. That transitioning neutron star we just discussed. The one that flips between accretion and pulsar modes. For years, astronomers assumed the X-rays came from the accretion disk. Hot gas, spiraling inward, friction heating it to millions of degrees. Standard model, textbook physics. But in 2024, NASA's IXB telescope looked more carefully. IXB doesn't just detect X-rays. It measures their polarization, the direction of the electric field oscillation, and the polarization told a different story. The X-rays weren't coming from the disk. They were coming from somewhere else. A pulsar wind. Particles accelerated by the spinning magnetic field, streaming outward, slamming into the accretion disk. The collision, the shock, produces X-rays, not the disk itself, but the wind hitting the disk. A completely different mechanism, a shift in understanding. The models had to be revised, textbooks updated. Our picture of the system changed. This is how science works. Assumptions tested, models revised, understanding evolving. We think we know, then we look more carefully, and we learn we were wrong or incomplete. That's okay. Being wrong is how we improve, how we learn. Your assumptions about sleep might be wrong too. You might think you can't sleep. That rest won't come. But look more carefully. Feel more deeply. The mechanism might be different than you think. Rest is approaching. From an unexpected direction, perhaps. But approaching. Let the surprise happen. Let the unexpected arrive. Let sleep from whatever source come. Most neutron stars accrete at modest rates. Gentle feeding. Steady streams of gas. But some feed voraciously. P13. A neutron star in the galaxy NGC 7793. About 12 million light years away. It accretes at supercritical rates. More material falling than the neutron star can easily handle. The accretion is so intense, the radiation pressure, the outward push from the X-rays is enormous. In normal accretion, material spirals inward in a flat disk, smooth, planar, but at supercritical rates, the disk is disrupted. Radiation pressure pushes material upward, downward, out of the plane. Tall columns form, towers of inflowing gas, rising above and below the disk. These columns pulse. The X-ray emission varies. Bright, dim, bright again. And the accretion, the extreme accretion, spins up the neutron star rapidly. In 2022, P13 rebrightened. After a faint period, it suddenly blazed. The X-ray luminosity soared, 100 times brighter, more, and the spin rate doubled. The neutron star spinning faster and faster, fed by the torrent of inflowing material, its feeding frenzy, cosmic gluttony, the neutron star consuming everything it can. Extreme, intense, powerful, but you don't need intensity. You don't need extreme. You need gentleness, modest rest, steady sleep. Let the frenzy exist far away, in another galaxy, while here, gently you rest. P13 wasn't always so bright. For years, it was quiet, faint, almost invisible, a sleeping neutron star, accreting very slowly, barely glowing. Astronomers observed it occasionally, monitoring, waiting, and in 2025, it woke up. The X-ray output increased dramatically, over 100 times brighter than before. Material from the companion star suddenly began flowing more rapidly. The accretion rate surged. The neutron star, dormant for years, roared back to life. Its spin accelerated. The accretion torque spun it up. Faster, faster. Astronomers watched, fascinated. This was rare. A neutron star waking up. In real time, they observed across wavelengths. Radio, X-ray, optical, capturing the awakening. The neutron star had been sleeping, and now awake, active, blazing. A transition from dormancy to activity, from quiet to loud. But the reverse happens too. Neutron stars that are active eventually quiet down, return to dormancy. The cycle continues. Wake, sleep, wake, sleep. You're in a cycle too. You've been awake, active, all day. Now, it's time for the other phase. Dormancy, quiet, rest. Let the cycle turn. Let activity fade. Let the neutron star of your consciousness, after its blazing day, dim into quiet, into dormancy, into sleep. Not every cosmic mystery has a clear answer. Some objects defy explanation. A SCAP J 1832-0657, a radio source discovered by the Australian Square Kilometre Array Pathfinder. It sits near a supernova remnant, close enough that it might be related, a neutron star perhaps, born in that explosion. But its properties are strange, eccentric. The radio emission is unusual. The timing doesn't match pulsar models. The spectrum is odd. For a while, astronomers thought it might be a neutron star, an unusual one, but a neutron star nonetheless. But further observations in X-rays with Chandra revealed more mysteries. The emission doesn't match neutron star expectations. The temperature is wrong. The variability is wrong. Now, The leading theory is that it's not a neutron star at all. It might be a white dwarf binary. Two white dwarfs orbiting, one with an extremely strong magnetic field, the strongest in the galaxy perhaps. But even this explanation has problems, uncertainties, gaps. The truth is we don't know, not for certain. It's an enigma. Some things resist understanding, defy categorization, remain mysterious. And that's okay. Not everything must be explained, solved, understood. Mystery is allowed in the cosmos and in your mind. You don't need to understand sleep to categorize your thoughts, to solve the enigma of consciousness. Just let mystery be. Let understanding fade. Let the unexplained exist in darkness, in sleep, in the beautiful unknown, among neutron stars. Magnetars are the most extreme. Their magnetic fields reach 10 to the 15th Gauss, a quadrillion times Earth's field. These fields are so strong, they distort the star itself. The crust, the solid outer layer, is stressed, twisted, deformed by magnetic pressure. Eventually, the crust can't take it. It fractures, cracks. A starquake, the magnetic field, suddenly released from its constraints, reconfigures violently, reconnects, snaps. Enormous energy is released in gamma rays, X-rays, particle beams, a magnetar flare. These flares are visible across the galaxy, even in extreme cases, across intergalactic space. On December 27, 2004, a magnetar flare from SGR 1806 to 20 reached Earth. The magnetar was 50,000 light years away, on the far side of the galaxy. But the flare was so intense, it ionized Earth's upper atmosphere, disrupted radio communications, affected satellites. For a tenth of a second, that distant magnetar outshone the full moon in gamma rays. If it had been closer, just a few thousand light years, the effect on Earth might have been catastrophic. But it wasn't. We were safe, far enough away. Magnetars are rare, violent, powerful, but also far away. Let them exist in the distance. Let their violence remain remote, while you here safe rest. No starquakes, no flares, just gentle quiet. Deep inside a neutron star, in the crust, pressure is extreme. Carbon atoms found in the outer layers are compressed. On Earth, carbon under pressure becomes diamond, the hardest natural material. Beautiful, crystalline. In a neutron star crust, the pressure is billions of times greater. Some models suggest, some calculations predict that carbon might form diamond layers, sheets of diamond, crystalline structures, extending through the crust, or perhaps diamond rain, droplets of liquid carbon, cooling, crystallizing, falling downward through the crust layers, raining diamonds. Inside a neutron star, it's speculative, theoretical, We can't observe it directly, can't test it, but the physics allows it, perhaps even requires it. Imagine a star made partly of diamond, the most valuable substance on Earth, common inside a neutron star, beauty hidden inside extreme violence, gems formed by crushing pressure. The universe creates wonders in unexpected places, under conditions we can barely imagine. You contain wonders too, hidden, interior, created by pressure, by life's compressions. Those wonders exist whether you see them or not, whether you acknowledge them or not. Rest now. Let the hidden diamonds of your being simply exist, unseen, valuable, real, in the darkness, in the depths, diamond layers asleep. What if a neutron star could exist inside another star, not orbiting it, not near it, but literally inside, at the core? This is a Thorne-Zitko object, named after Kip Thorne and Anna Zitko, who proposed the idea. A giant star, red supergiant perhaps, with a neutron star at its center instead of a normal core. How would this form? Start with a binary system. A neutron star orbiting a giant star. The orbit decays. They spiral inward. Eventually they collide. But instead of merging completely, the neutron star survives. It plunges into the giant's envelope, sinks to the center, and remains there, orbiting inside the star, or settled at the core. The giant star continues shining, but now powered differently. The neutron star accretes material, releases energy. The star's chemistry changes. Elements produced in unusual abundances. Rapid neutron capture. S-process elements. A few candidate Thorne-Zitko objects have been identified. Stars with unusual spectra. Too much of certain elements. But confirmation is difficult. The signature is subtle, ambiguous. These objects, if they exist, are rare, transient. They might last only thousands of years before the giant exhausts itself. A star within a star, a nested structure, levels of being. You have levels too. Consciousness, subconsciousness, deep structures beneath awareness, one nested inside another, all coexisting, all real. Let the outer layers fade. Let awareness sink inward to the deeper core, the nested quiet where sleep waits, patient at the center. In 1974, Russell Hulse and Joseph Taylor made a discovery. PSR be 1913 plus 16, a pulsar, but not alone. In a binary system, the orbital period, 7.75 hours. The orbit, eccentric, elliptical. The pulsar's timing varied, periodically, due to its orbital motion, Doppler shift. By carefully measuring these timing variations, Hulse and Taylor could determine the orbit precisely, mass of the pulsar, mass of the companion, orbital parameters, everything. And then they noticed something remarkable. The orbital period was decreasing, shortening by about 76 microseconds per year. The orbit was decaying, the two objects spiraling closer together. Why? General relativity predicts this. Orbiting masses generate gravitational waves, ripples in space-time. These waves carry energy away. As energy is lost, the orbit shrinks. Einstein's theory makes specific predictions: how much energy, how fast the decay, and the observations matched perfectly to parts per thousand. This was the first indirect detection of gravitational waves, proof that they exist, that general relativity is correct. In 1993, Hulse and Taylor received the Nobel Prize in Physics for watching, measuring, patiently, over years, and confirming the universe behaves as Einstein predicted. Patience reveals truth, long observation, careful measurement. Your journey to sleep requires patience too. Observation of your own settling, measurement of your own decay into rest. Let the orbit shrink. Let energy drain away. Let gravitational waves of drowsiness carry you closer to sleep. The Hulse-Taylor binary continues to decay. Even now, 50 years after discovery, the orbit has shrunk measurably, perceptibly, millimeters per year. Tiny, but real. Over decades, those millimeters add up. The orbital period 17.75195 hours is now 7.75194 hours. A tiny change, but measurable, and it matches general relativity's predictions to extraordinary precision, parts per thousand. The theory and observation agree almost perfectly. This is one of the best confirmations of general relativity we have. Indirect, but powerful. The binary will continue spiraling inward for millions of years. Gradually, eventually, hundreds of millions of years from now, the two neutron stars will merge. The orbit will shrink to zero. The stars will collide, explode perhaps, or form a black hole, a catastrophic end, but far in the future. For now, just slow decay, patient, inevitable, measured. Everything decays eventually. Energy dissipates. Orbits shrink. Systems wind down. This is entropy. The second law, universal, inescapable. Your wakefulness is decaying too. Energy dissipating. The orbit of consciousness shrinking. Let the decay continue. Let the shrinkage proceed. Let the inevitable approach. Into merger. Into collapse. Into sleep. In 2003, astronomers made an extraordinary discovery. PSR J0737-3039, a binary system, two neutron stars, orbiting. But here's what makes it unique. Both are pulsars. Both emit radio pulses. Both are detectable from Earth. This is incredibly rare. Usually, only one neutron star in a binary is oriented correctly. Its beam sweeps past Earth. the other doesn't. But in this system, by extraordinary coincidence, both beams sweep past us. We see both pulsars, pulsing at different rates, different angles. This allows unprecedented tests of general relativity, 5 different tests, 5 predictions of the theory, all measurable in this one system: gravitational redshift, time dilation, orbital decay, Shapiro delay, geodetic precession, all predicted by Einstein, all measured, all matching perfectly. The double pulsar is a natural laboratory, testing the limits of our understanding, probing the nature of space-time. And so far, general relativity passes every test. Perfectly, 2 pulsars, sweeping their beams, marking time for the cosmos, teaching us truth. Your mind has 2 voices too, conscious and unconscious, both present, both real. As you drift asleep, the conscious voice fades. The unconscious strengthens. 2 beams, one dimming, one brightening. Let the transition complete. Let the double system of your mind find new balance. Conscious fading, unconscious rising, sleep arriving. And with this final fact, this 90th window into neutron stars, let us conclude you've journeyed far tonight, through birth and death, through spin and slowdown, through ordinary pulsars and exotic magnetars, through binaries and triples, through mysteries and confirmations. The neutron stars continue their dance, spinning in the darkness, sweeping their beams across the galaxy, testing the limits of physics, revealing the nature of matter at its most extreme. But for you, the journey ends here. The observations conclude. The measurements cease. It's time to stop learning, stop thinking, stop observing. It's time, finally, after 90 fact and 4 hours of gentle drift, to sleep. The universe will continue without your attention. The neutron stars will spin. The binaries will orbit. The magnetars will flare. All without you. All while you rest. Let go of the cosmos. Let go of neutron stars. Let go of everything. Just sleep, deep, peaceful, restorative. Thank you for this long journey through the densest objects in the universe. May your sleep be as deep as their cores, as peaceful as their slow spin down, as complete as their rest. Good night. Sleep well, and may the lighthouse beams of neutron stars somewhere far away continue to pulse while you dream. General relativity predicts something strange, something called frame dragging. When a massive object spins, it doesn't just curve space around it, it drags space-time itself, twisting it, rotating it, like a marble spinning in honey. The honey near the marble dragged along, rotating with it. For Earth, this frame dragging is tiny, imperceptible, but measurable. Satellites have detected it. For a neutron star, spinning hundreds of times per second, the frame dragging is much stronger, And in a binary system, when a neutron star orbits another dense object, the frame dragging affects the orbit itself. PSR J1141-6545, a pulsar orbiting a white dwarf companion. The pulsar's spin, dragging space-time, twists the orbital plane. Gradually, measurably, this is called gravimagnetism. Gravity acting like magnetism, rotating fields, dragging effects by carefully timing the pulsar, measuring tiny variations in pulse arrival. Astronomers can detect the frame dragging and compare to general relativity's predictions. So far, the theory holds. The measurements match perfectly. Space-time really does twist, really does drag, just as Einstein said. The universe is stranger than it appears. Space and time are not rigid. They bend, they twist, they flow, like honey, like fabric, dragged by spinning mass. Your sense of time is twisting too, dragging, slowing. Minutes feel longer, hours compress. The rigid structure of wakefulness, bending, let space-time twist around you. Let time drag slower. Let the frame of consciousness rotate into sleep. If a neutron star is perfectly spherical, perfectly symmetric, it rotates smoothly, quietly. But if there's an asymmetry, a mountain on the surface, a bulge, the rotation becomes uneven. Mass moves in an asymmetric pattern, around and around, like an unbalanced washing machine. And in general relativity, accelerating mass produces gravitational waves. A perfectly symmetric neutron star produces none. But an asymmetric one, even slightly, produces a continuous hum, a gravitational wave signal, very weak, very faint, but potentially detectable. Current gravitational wave observatories like LIGO listen for these signals. So far, none confirmed, but upgrades are coming. More sensitive detectors, longer observation times. In the future, we might detect continuous hum of a misshapen neutron star, vibrating space-time, singing in gravity. The signal would tell us about the surface, the mountains, the asymmetries, how rigid the crust is, how the star deforms. Everything vibrates, everything sings, even space itself. Your body vibrates too. Heartbeat, breath, muscles trembling slightly, neurons firing, a continuous hum of life, usually unnoticed, but always present. As you settle into sleep, the vibrations slow, the hum deepens, the frequency drops. Let the gravitational waves of your being soften. Let the asymmetries settle. Let the continuous signal fade into the background, into quiet, into stillness, into sleep. When two neutron stars orbit closely, just before merger, they exert tidal forces on each other, like the moon raising tides on Earth. But far more extreme, the tidal forces try to stretch each neutron star, deform it, elongate it toward its companion. How much the star deforms depends on its internal structure, its stiffness. A stiff neutron star with a hard equation state resists deformation, stays nearly spherical. A soft neutron star with a compressible equation of state deforms more easily, becomes elongated. This deformability, called tidal deformability, affects the gravitational wave signal. When LIGO and Virgo detected GW170817, the neutron star merger, they measured the waveform precisely. The final moments before merger, the orbital frequency, the amplitude, and from this, they extracted the tidal deformability, how much the stars deformed. The measurement constrained the equation of state, ruled out the very stiffest and very softest models, narrowed the possibilities, improved our understanding. Two stars, deforming each other, dancing closer, teaching us about matter at nuclear density. In their final moments, as they touched, as they merged, they revealed their inner nature. You're deforming too, your body molding to the mattress, your mind reshaping towards sleep. Let the deformation continue. Let stiffness fade. Let resistance dissolve. Soft, malleable, yielding to gravity, to tiredness, to sleep. When neutron stars merge, when they collide and combine, the resulting object vibrates like a bell struck or a drum hit. It rings. The merged remnant, perhaps a hypermassive neutron star, perhaps already a black hole, oscillates. These oscillations have characteristic frequencies, modes of vibration. The fundamental mode, called the F mode, vibrates at about 2 kilohertz, 2,000 cycles per second, a high-pitched tone. If we could hear gravitational waves, a ringing, brief, fading quickly, these oscillations encode information about the merged object's mass, its radius, its equation of state. Future gravitational wave detectors, more sensitive than current ones, might detect these post-merger vibrations, the ringing after collision, the echo of merger, and from that ringing, we could learn about matter at its absolute limit, the edge of collapse, the boundary between neutron star and black hole. Everything rings when struck. Everything has modes of vibration, natural frequencies. Your mind rings too, struck by thoughts, vibrating at the frequency of consciousness. As you drift asleep, the ringing quiets, the vibrations slow, the modes damp out from 2 kilohertz to 1 to 0.1 to silence. Let the ringing fade. Let the oscillation cease. Let the F mode of wakefulness decay into stillness. Simulating neutron star mergers is incredibly difficult. The physics is complex. General relativity, hydrodynamics, nuclear physics, magnetic fields. Computers must solve Einstein's equations, track millions of particles, simulate microseconds of real time. Even the most powerful supercomputers struggle. Simulations typically run for milliseconds, maybe a few milliseconds. The merger happens, the collision, the initial dynamics. Then the simulation ends. Too expensive to continue. But in 2025, a breakthrough. New algorithms, better computers, improved methods. A simulation that ran longer than ever before. Seconds, not milliseconds. Seconds, long enough to see what happens after merger, the remnants evolution, the black hole birth if it collapses, the jets that might form, long enough to make predictions for gamma-ray telescopes, for gravitational wave detectors, for optical telescopes watching kilinovae, multi-messenger astronomy, observing the same event across all wavelengths, all messengers. The simulation guides observers, tells them what to look for, when, how bright, step by step, millisecond by millisecond. The simulation reveals what theory predicts. Your drift into sleep is a simulation too. Your brain running algorithms, predicting rest, guiding you inward, step by step, breath by breath. The simulation runs, longer than before perhaps. Let the simulation continue. Let the algorithms execute. Let the prediction of sleep become reality. When two neutron stars spiral together, their magnetic fields interact. Each star has its own field. Strong, organized, dipolar perhaps. But as they approach, the fields tangle, twist around each other, reconnect. Magnetic field lines snap, reconfigure, release energy. 2025 simulations explored this tangling, these magnetospheric interactions, and they found something remarkable before the actual collision. In the final moments of inspiral, the tangled fields might produce detectable radiation, gamma rays, X-rays, radio bursts perhaps, signals that arrive before the gravitational wave merger signal, precursors, warnings. Future wide-field telescopes, watching the sky continuously, might detect these precursor signals and alert gravitational wave detectors. Look here, a merger is about to happen. Watch. The fields tangle, the stars approach, the signals announce. The collision follows. Everything connected, everything signaling, everything linked. Your neural fields are tangling too, thoughts crossing, memories interweaving, consciousness and subconsciousness merging. The signals are fading, the precursors of sleep, yawns, heavy eyelids, wandering attention. Let the fields tangle completely. Let the boundaries dissolve. Let merger of wake and sleep complete. August 17th, 2017. A date in astrophysics history. LIGO and Virgo detected gravitational waves. GW170817. Two neutron stars merging. The signal lasted 100 seconds. As the stars spiral closer, faster, until collision. But this time, Unlike previous detections, there was more. Gamma ray satellites detected a short gamma ray burst, GRB 170817A, 2 seconds after the merger, and then, hours later, optical telescopes found a new light source in the galaxy in GC 4993, a kilonova, a bright explosion, not a supernova, different, redder, evolving differently. The light came from radioactive decay, heavy elements, freshly synthesized in the merger, neutron-rich nuclei, decaying, glowing. Over days, the kilonova faded, changed color, red to infrared, as ejecta cooled. This was confirmation, proof that short gamma ray bursts, mysterious flashes in the sky, come from neutron star mergers. Decades of theory, finally confirmed in a single event. 3 messengers, gravitational waves, gamma rays, optical light, all from one collision. Multi-messenger astronomy, the future of astrophysics, understanding events through all channels, all wavelengths, all signals. You experience reality through multiple channels too. Sight, sound, touch, thought, emotion, but in sleep the channels close. One by one, sight dims, sound fades, touch softens, until only one remains, the internal channel. Dreams, or nothing, let the channels close. Let the messengers cease. Let only darkness, only silence remain. Short gamma ray bursts have been a mystery for decades. Brief flashes, lasting less than 2 seconds, coming from random directions in the sky. Incredibly bright, energetic, but over quickly. What could produce them? Many theories existed. Colliding neutron stars. Neutron stars swallowed by a black hole. Magnetar flares. But no proof, no direct observation linking a burst to a specific source until GW 170817 and GRB 170817A. The gravitational wave said, neutron star merger, here, at this time. The gamma rays said, short burst, here, at this time. 2 seconds later, the same event, confirmed, linked, proven. Neutron star mergers, at least some of them, produce short gamma ray bursts. The mechanism is still being studied. Jets perhaps launched from the merger remnant, boring through the debris, breaking free, emitting gamma rays, but the connection is confirmed. The origin known. 3 phenomena. Binary neutron stars, kilonovae, short gamma ray bursts, all connected, all one event, mystery solved, understanding achieved, through patient observation, multi-messenger detection. Mysteries can be solved with patience, with attention, with the right instruments. Your mystery tonight is simple. How to sleep. The instruments are here. Your body, your breath, your mind, The solution is approaching, the connection being made between wakefulness and rest. Soon confirmed, proven, achieved. Sleep. When neutron stars merge, they don't just release energy. They create matter, new elements, heavy elements, elements that cannot form in normal stars. Gold, platinum, uranium, rare earths. These elements require rapid neutron capture. The R process, atomic nuclei bombarded by neutrons, absorbing them, one after another, rapidly, before they can decay, before they stabilize. This only happens in extreme environments. High neutron density, high temperature, high energy. Neutron star mergers provide exactly these conditions. In the ejected material, the debris sprayed out during collision, neutrons are abundant. Nuclei capture them, build up, become heavier, heavier, climbing the periodic table. From iron to silver to gold to platinum to uranium. The R process creates about half of the elements heavier than iron. The other half comes from supernovae. Every gold ring, every platinum catalyst, every uranium fuel rod came from stellar collisions, violent mergers, ancient explosions. The gold in your jewelry, forged in the collision of neutron stars. Billions of years ago, in some distant galaxy perhaps, then scattered into space, incorporated into new stars, new planets, eventually Earth, and now on your finger, in your phone, in circuits and components, neutron star collisions, creating the elements of civilization. You're made of stardust. Truly, the iron in your blood, the calcium in your bones, the gold in your ring, all forged in stellar furnaces, in supernova explosions, in neutron star collisions. You are the universe, condensed, aware, resting. Let the ancient elements of your being settle. Let the gold and iron and calcium rest. As you forge in cosmic violence, peacefully sleep, we've reached the final fact. The 100th window into neutron stars. And perhaps the most important, neutron stars are laboratories, natural laboratories, for physics at its most extreme. Nuclear density, matter compressed to the limits of stability, where neutrons touch, where quarks might emerge. We cannot create such conditions on Earth. No laboratory can. The pressures are too high. The energy's too great. Ultra-strong gravity. Space-time curved to near the black hole limit, where general relativity is essential, where Newtonian gravity fails completely. We can test Einstein's theory. In the strongest fields accessible, short of black holes, magnetic fields beyond anything we can produce, quadrillions of times Earth's field, where quantum electrodynamics behaves strangely, where vacuum itself becomes magnetized, we can study how light propagates, how particles move, how fields interact. These are natural laboratories. provided by the universe, free, accessible if we can observe them, and we can, with telescopes, gravitational wave detectors, gamma-ray satellites. We watch, we measure, we learn about matter, about gravity, about magnetism, about the fundamental forces. Neutron stars teach us. They reveal the universe's secrets, the laws that govern reality. By studying the most extreme, we understand the everyday. By observing the bizarre, we comprehend the normal. This is why we look up, why we observe, why we build telescopes and detectors. To learn, to understand, to know, and now, 100 facts, 100 glimpses into neutron stars, from their violent birth in supernovae to their quiet aging over billions of years, from their crushing density to their diamond cores, from their millisecond spins to their eventual silence. You've journeyed through pulsars and magnetars, through binaries and mergers, through glitches and gamma-ray bursts, through the densest, strangest, most extreme objects in the universe. And through it all, you've been settling, slowing, drifting towards sleep. The journey is complete. The 100 facts told. The neutron stars explained, as much as current knowledge allows. Now let the knowledge fade. Let the facts blur. Let the neutron stars spin, far away, without your attention. You've learned enough, more than enough. Your mind is full, satisfied, ready to rest. Let the laboratories of the universe continue their experiments. Let the natural physics proceed. Let the cosmos teach, while you sleep. 100 facts, complete, finished, and so your wakefulness, complete, finished. Thank you for this long, patient journey through the strangest corners of astrophysics, through the densest objects in existence. May your sleep be as deep as their cores, as peaceful as their slow evolution, as complete as their rest. May you dream of spinning stars, of cosmic collisions, of gold forged in violence, of diamonds under pressure. Or may you dream of nothing, blank, quiet, dark. Either way, sleep. Finally, after 5 hours, after 100 facts, sleep. The neutron stars will continue spinning. The binaries will continue orbiting. The mergers will continue creating gold. All without you. All while you rest. Good night. Sleep deeply. And may the universe, in all its extreme glory, watch over you, while you peacefully, completely sleep